Imagine a region of space where time stands still, where gravity pulls everything into an abyss, and where mysterious forces shape the very fabric of the universe. This is the realm of extraordinary cosmic anomalies, where the rules we know about physics seem to unravel. Join us as we dive into this captivating exploration, challenging everything we think we know about the cosmos. The defining characteristic of a black hole that gives it an unsettling reputation is its gravitational pull. A black hole is formed when a massive star exhausts its nuclear fuel and collapses under its own gravity, compressing its mass into an incredibly small point, known as a singularity. Surrounding this singularity is a boundary called the event horizon. This is the point of no return. Once any matter crosses this threshold, it cannot escape the intense gravitational grip of the black hole. What makes black holes particularly fascinating and frightening is their ability to attract and consume everything in their vicinity, including light. This means that while we cannot see a black hole directly, we can observe its effects on nearby stars and gas. When matter gets pulled toward a black hole, it accelerates and heats up, emitting X-rays that we can detect with telescopes. This phenomenon allows us to infer the presence of these enigmatic objects even from vast distances. Furthermore, the idea of being drawn into a black hole evokes visceral fear. Imagining a fate where one is stretched and compressed by gravitational forces, a process scientists describe as spaghettification, adds to the mystery and horror of these cosmic entities. It also raises profound questions about the nature of space and time. Near a black hole, the fabric of space-time is warped, leading to a distortion that defies our ordinary experiences. The terrifying allure of black holes derives not just from their powerful pull, but also from the mysteries they embody. They challenge our understanding of physics, offering a glimpse into realms where the normal rules seem to break down. As we study these fascinating phenomena, we uncover more about the universe and our place within it, igniting both wonder and apprehension. Detecting black holes might seem like trying to find a phantom in the night, but scientists have developed clever methods to uncover their presence. Because black holes do not emit light, they cannot be seen directly with telescopes. Instead, astronomers look for the effects that black holes have on their surroundings. A powerful way to spot a black hole is through the observation of nearby stars and gas that are influenced by its gravity. When a black hole is in a binary system with another star, it can draw matter from that star. This process creates an accretion disk, a swirling mass of gas and dust that spirals into the black hole. As the matter falls, it heats up to extremely high temperatures, producing X-rays that are detectable by specialized space telescopes. In this way, scientists can identify the black hole by the radiation emitted from the accretion disk, even if the black hole itself remains hidden from view. Another intriguing method of detection involves observing gravitational waves. By infrastructure such as the Laser Interferometer Gravitational Wave Observatory, scientists can detect ripples in space-time caused by the merging of black holes. When two black holes collide, they create a tremor that travels across the universe, and these gravitational waves tell us a lot about their properties, such as mass and spin, even if the black holes themselves are not visible. Lastly, black holes can have a profound impact on their environment, such as influencing the motion of stars in their vicinity. By studying the orbits of these stars, astronomers can infer the presence of a black hole based on the gravitational pull it exerts. This combination of observing X-rays, measuring gravitational waves, and analyzing the orbital motions of stars allows scientists to detect and study these enigmatic giants lurking in the cosmos without ever seeing them directly. When matter and energy cross the event horizon of a black hole, they enter a region from which nothing can escape, not even light. This boundary marks the point of no return. The moment an object crosses this threshold, it is pulled inexorably toward the center of the black hole, where the gravitational pull becomes overwhelmingly strong due to the black hole's immense mass concentrated in a very small volume. What actually happens to that matter as it falls into the black hole remains one of the great mysteries of modern astrophysics. Classical physics predicts that matter gets crushed to an infinitely small point known as a singularity. At this point, the laws of physics as we understand them no longer apply. Everything that falls into a black hole, from stars to gas clouds to entire planets, is thought to be compressed into this singularity, where densities become incomprehensibly high. Meanwhile, the energy associated with the infalling matter may not vanish. As matter spirals into the black hole, it forms an accretion disk, a swirling mass that generates tremendous friction and heat, releasing energy in the form of radiation. This process can result in powerful jets of particles being expelled from the black hole's poles, which can be observed as bright bursts of light and radiation. It's a fascinating paradox. As things are drawn in, they can also create effects that can be seen far outside the event horizon. Philosophically, the fate of matter that crosses the event horizon raises intriguing questions about information. According to quantum mechanics, information cannot be destroyed. This notion leads to what is known as the information paradox, which is a topic of ongoing research and debate among physicists. So, while we may not fully understand the final destination of matter and energy that crosses a black hole's event horizon, we continue to explore its implications for our understanding of the universe. Spaghettification, a term that sounds as whimsical as it is alarming, describes the extraordinary effects of gravity on objects that venture too close to a black hole. As one approaches the black hole, the gravitational force can vary dramatically depending on proximity. The result is a process where objects are stretched and compressed. Imagine a person falling gently toward a black hole. The gravity pulling on their feet would be much stronger than that acting on their head. The outcome? They would be elongated, much like a piece of spaghetti. This phenomenon occurs because black holes exert powerful gravitational forces. When an object crosses the boundary known as the event horizon, there is no returning. All light and information are trapped beyond this point. The implications of spaghettification are profound. For an astronaut or any object daring to approach, it would mean a violent yet fascinating end, getting pulled apart atom by atom. Even the strong forces that hold atoms together cannot withstand the tidal forces created by the black hole's gravity. Interestingly, spaghettification isn't exclusive to black holes. It can also occur near neutron stars, which are incredibly dense remnants of supernova explosions. Similar extreme gravitational forces arise near these celestial objects, stretching any matter that strays too close. This highlights that the universe, while beautiful and awe-inspiring, is also fraught with dangers waiting in the depths of space. In contemplating spaghettification, we gain insights into the extreme environments of the cosmos and the boundaries of physical law. It embodies the intense gravitational drama of the universe, where normal rules no longer apply, and the bizarre becomes ordinary. While it might seem terrifying, it also underscores the splendor and strangeness of our universe, inviting us to ponder the mysteries of black holes and the vast unknown awaiting us in the night sky. Black holes, the enigmatic giants that lurk at the center of many galaxies, continue to astonish us with their peculiar behaviors and unexpected characteristics. One of the most eerie observations is that the mass of a supermassive black hole is often correlated with the properties of its host galaxy. This seems to suggest a deep connection between the formation of galaxies and the growth of black holes, with the two evolving together over billions of years. For scientists, this raises a chilling question. Do black holes influence the structure and fate of galaxies, or vice versa? Another bizarre phenomenon observed is the presence of black holes that are surprisingly massive for the size of their host galaxies. In some cases, astronomers have detected black holes with masses millions to billions of times greater than that of our Sun, nestled within dwarf galaxies. These findings push our understanding of cosmic evolution to its limits. Why would such a hefty black hole form in a relatively small galaxy? It remains one of the great mysteries of modern astrophysics and speaks to the potentially bizarre and chaotic history of our universe. Furthermore, we have seen evidence of black holes ejecting powerful jets of particles at nearly the speed of light. These jets can stretch across millions of light years, far beyond the immediate vicinity of the black hole itself. This aligns with observations of quasars, which are highly luminous objects powered by supermassive black holes consuming material. The violent nature of these jets challenges our understanding of how matter behaves in such extreme environments and raises questions about the influence black holes exert on their surroundings. Lastly, scientists have also detected strange ripples in spacetime caused by black holes merging. These gravitational waves not only provide insight into the nature of black holes, but also challenge our understanding of the fabric of the universe itself. Each merger emits energy equivalent to the mass of several suns converted into gravitational waves, allowing us to hear them in ways we never imagined possible. Such discoveries remind us of the hidden and often eerie realities of our universe, where black holes serve as both objects of fascination and key players in the cosmic drama. Black holes represent one of the most fascinating puzzles in modern physics. At their core, these mysterious objects are regions of space where gravity is so strong that nothing, not even light, can escape. This extreme gravitational pull leads to profound questions about the nature of space and time. The boundary surrounding a black hole is called the event horizon, and once something crosses it, there's no turning back. The very existence of these celestial phenomena challenges our understanding of the universe on multiple levels. One of the primary ways black holes test our grasp of physics is through the conflict between general relativity and quantum mechanics. General relativity, which explains gravity as the warping of spacetime by mass, predicts that black holes can form and behave as described. However, when we delve into the quantum realm, where particles exist and interact, the laws that govern this tiny world operate quite differently. A significant conundrum arises when trying to reconcile the two theories, particularly regarding what happens to information that falls into a black hole. This leads to the so-called information paradox, where some physicists argue that information may be lost forever, contradicting fundamental principles of quantum physics that state information must be conserved. Additionally, the very nature of singularities within black holes poses further challenges. A singularity is a point at which the density of matter and gravitational forces become infinite, and our current laws of physics break down. This raises essential questions about the behavior of matter and energy under such extreme conditions. How can science describe the fabric of reality when its most fundamental laws seem to falter in these bizarre environments? Researchers continue to explore these mysteries, pushing the boundaries of our understanding. The study of black holes not only deepens our insights into the fabric of the universe, but also compels us to consider new theories. For instance, concepts like quantum gravity aim to bridge the gap between general relativity and quantum mechanics. As we observe the universe's behavior and nature through the lens of black holes, we find ourselves on the brink of new discoveries that could reshape our fundamental understanding of the laws of physics. Black holes, particularly supermassive black holes found at the centers of galaxies, are thought to play a crucial role in the formation and growth of galaxies. As galaxies form and evolve, these black holes can influence their surroundings through powerful gravitational forces. The process begins when gas and dust from the galaxy fall toward the black hole, creating an accretion disk. As material spirals in, it heats up and emits vast amounts of energy, which can affect star formation rates in the galaxy. This interaction can trigger bursts of star formation or even inhibit it, showcasing a delicate balance in the relationship between galaxies and their central black holes. As these black holes grow, they can merge with others during galaxy collisions, becoming larger and even more influential. This merger process can shape the structure of galaxies in profound ways. An expanding black hole may cause large swathes of gas to be expelled from the galaxy, a phenomenon known as feedback. This feedback regulates star formation and affects the overall evolution of the galaxy, suggesting that black holes are central players in the cosmic dance of creation and destruction. Now, when we consider the future of our universe, the implications of black holes become concerning. As they grow and consume surrounding matter, they may contribute to a universe that is gradually losing its ability to form stars. Over vast stretches of time, as galaxies merge and their supermassive black holes continue to grow, the available gas and dust to fuel new stars diminishes. The very engines of growth begin to extinguish the light of new stars, leading us to a universe that is increasingly dark and devoid of new celestial life. Moreover, as black holes grow in mass, they could stabilize their galaxies in ways that make them less prone to interacting with one another or creating new stars. Consequently, we face a future where, as black holes dominate the cosmos, galaxies drift into a stagnant state. The cosmic landscape may shift into one characterized by aging stars, with fewer signs of stellar births, an eventuality that paints a rather somber picture for the long-term fate of our universe. In this way, black holes serve not only as fascinating celestial objects, but also as harbingers of a quiet, dim future for galaxies. Yes, there are indeed types of black holes beyond the well-known stellar and supermassive categories. When most people think of black holes, they often picture stellar black holes, which form from the remnants of massive stars after they explode in supernova events. Then there are supermassive black holes, which lurk at the centers of galaxies and can have masses equivalent to millions or even billions of suns. However, the universe is full of surprises, and so are the types of black holes that exist within it. One fascinating category is known as intermediate black holes. These black holes are thought to have masses ranging from 100 to 100,000 times that of our Sun. While we don't fully understand how they form, some theories suggest that they could be the result of the merging of smaller black holes or the collapse of massive star clusters. Excitingly, evidence for these intermediate black holes has begun to surface, indicating they might be more common than originally thought. Another intriguing possibility is the existence of primordial black holes. These are believed to have formed shortly after the Big Bang, arising from density fluctuations in the early universe. Primordial black holes could vary greatly in size, some possibly as small as a mountain, while others could be much larger. The existence of these black holes could explain many phenomena that remain mysterious in cosmology, such as dark matter. Lastly, there are hypothetical black holes that fall outside conventional boundaries, such as nano-black holes and supersized versions that challenge our understanding of physics. While evidence for these types remains elusive, scientists continue to explore and theorize about their existence. Each type of black hole deepens our understanding of the universe and its complexities, revealing just how much we have yet to learn. Black holes, those enigmatic cosmic phenomena, hold many mysteries about their formation and nature. They begin as massive stars, which exhaust the nuclear fuel in their cores. When the energy that counteracts gravity diminishes, the star can no longer support itself and collapses under its own weight. This collapse compresses matter into an incredibly small volume, resulting in gravitational forces so strong that not even light can escape. This is why we call them black holes. But why are researchers captivated, and sometimes frightened, by these celestial wonders? One key mystery surrounding black holes is their formation in various contexts. While most black holes form from dying stars, there are whispers of other types. Supermassive black holes, found at the centers of galaxies, may have evolved from the mergers of smaller black holes, or could have formed very early in the universe's history by gathering vast amounts of surrounding matter. Each new discovery raises more questions, expanding the boundaries of our understanding of the universe itself. Another layer of intrigue comes from the implications of black holes for our understanding of time and space. They challenge the very fabric of physics as we know it. For instance, the event horizon, the boundary beyond which nothing can escape, represents a point of no return. What lies beyond? As we delve deeper into the nature of black holes, we confront intense ideas that may defy our current understanding of reality, which can be intimidating to scientists and laypeople alike. It suggests that the universe can operate through rules we have yet to fully comprehend. Moreover, black holes serve as reminders of our limitations in exploring the cosmos. They are not just voids, but powerful forces that might distort our understanding of fundamental concepts like gravity and quantum mechanics. As each new revelation unfolds, scientists find themselves standing at the brink of profound discoveries, caught between excitement and a healthy sense of caution. Exploring these mysteries pushes our scientific boundaries while reinforcing the idea that the universe is filled with phenomena we are only beginning to understand. Dark matter is an enigmatic substance that constitutes about 27% of the universe. Unlike ordinary matter, which makes up the stars, planets, and all visible objects, dark matter cannot be seen directly. It neither emits nor absorbs light, making it invisible to our instruments that rely on electromagnetic radiation. Despite its unseen nature, scientists have inferred its existence through its gravitational effects on galaxies and galaxy clusters. One of the most compelling pieces of evidence for dark matter comes from observing how galaxies rotate. The outer edges of galaxies spin at speeds that, based on the visible matter alone, should cause them to fly apart. However, they remain intact, indicating that a significant amount of unseen mass must be present, providing the gravitational pull needed to hold them together. This invisible glue is what we call dark matter. The reasons dark matter feels mysterious and even a bit frightening are twofold. First, it defies our understanding of matter and energy as we know them. Our universe is built on atoms and particles, yet dark matter does not correspond to any of those familiar entities. Second, dark matter poses profound questions about the very fabric of reality, challenging everything we thought we understood about the universe's composition. This mystery continues to inspire intense scientific inquiry. Countless researchers are engaged in experiments to identify the properties of dark matter and ultimately to discover what it is made of. As a leading player in the cosmic narrative, dark matter holds the key not only to understanding the universe's structure, but also to grasping the fundamental laws that govern it. The search for dark matter remains one of the most thrilling quests in modern astrophysics, continually pushing the boundaries of our knowledge. Dark matter is one of the universe's great mysteries, making up about 27% of everything we know exists. Although it is invisible and does not emit light, dark matter exerts a gravitational influence that shapes the cosmos on a grand scale. Its presence is fundamental in forming structures such as galaxies, clusters of galaxies, and the cosmic web that connects them. This web-like structure of the universe is a result of dark matter's gravitational pull, which serves as a framework where visible matter, like stars and gas, gathers and forms the galaxies we can observe. When we consider how galaxies form and evolve, it's clear that dark matter plays a pivotal role. Early in the universe's history, tiny fluctuations in density allowed dark matter to collapse and form clumps. These clumps acted like seeds, drawing in regular matter due to their gravitational attraction. As these ordinary materials accumulated, galaxies began to take shape around these dark matter halos. This means that every galaxy is like a bright island in a dark sea, with the dark matter providing the unseen structure and stability required for star formation and galactic activity. Moreover, dark matter influences not just the formation of galaxies, but their interaction as well. Galaxies are not isolated. They exist in clusters that can consist of hundreds or even thousands of galaxies. The gravitational pull of dark matter helps bind these clusters together, affecting their motions and the dynamics within them. Observations indicate that the majority of the mass in these clusters is in the form of dark matter, reinforcing its critical role in the universe's large-scale structure. Finally, the expansion of the universe itself is influenced by dark matter. While dark energy drives the accelerated expansion, dark matter helps slow it down through its gravitational effects. This complex interplay of forces highlights dark matter's vital role in maintaining the balance of the cosmos. The continued study of dark matter not only enhances our understanding of how the universe operates, but also inspires a deeper appreciation for the intricate dance of particles and forces that make up our vast universe. Dark matter, an elusive component of our universe, makes up about 27% of its total matter-energy content. Despite its prevalence, dark matter remains one of the greatest mysteries in cosmology. Various theories abound, each offering different candidates for this invisible substance, from exotic particles to modified gravity theories. One prominent theory proposes that dark matter consists of weakly interacting massive particles, or WIMPs. These hypothetical particles would interact with normal matter through gravity and perhaps through weak nuclear forces. Since they interact so weakly, they would be difficult to detect directly. Scientists have designed numerous experiments deep underground and even in space to try to catch a glimpse of these elusive entities, but so far they remain undetected. Another intriguing candidate is axions, extremely light particles thought to arise from certain theoretical frameworks in particle physics. Axions are peculiar because they could explain not only dark matter, but also certain peculiarities in the behavior of magnetic fields. If they exist, axions would form a kind of background energy field, subtly influencing the universe's structure without being noticed directly. Research into axions continues to unfold as scientists explore ways to discover these quirky particles. Additionally, there are theories that suggest dark matter might not be a particle at all, but rather an alteration in our understanding of gravity itself. Modified gravity theories propose that the laws of gravity as we know them may not apply at cosmic scales. These theories, such as MOND, suggest that we need to rethink our gravitational laws to account for the observed effects attributed to dark matter. Each theory presents a unique perspective on dark matter, reflecting the ongoing quest to unlock the secrets of our universe. The search is not just for answers, but for a deeper understanding of the cosmos that surrounds us. Dark matter is an elusive substance that makes up a significant portion of the universe, yet it does not interact with ordinary matter in the way we might expect. Unlike the atoms that compose the stars, planets, and ourselves, dark matter does not emit, absorb, or reflect light. This characteristic means that it cannot be detected by traditional means of observation, which rely on electromagnetic radiation. As a result, dark matter's presence is inferred indirectly from its gravitational effects on visible matter. This lack of direct interaction can imply several things about our cosmos. If dark matter were to interact with ordinary matter, even slightly, we might expect to see signs of this interaction in particle colliders or through various detection experiments. However, the minimal interaction suggests that dark matter particles are incredibly weakly interacting, or perhaps they have their own set of fundamental forces. Thus, while ordinary matter forms the building blocks of the stuff we see, dark matter operates under a different set of rules. Understanding dark matter's properties is vital for our comprehension of the universe's structure. It accounts for about 27% of the total mass energy content of the universe, influencing how galaxies form and bind together. The gravitational lensing effect, where light from distant objects bends around massive dark matter structures, is one of the clues astronomers use to map dark matter distribution across the cosmos. This complex interplay provides insight into evolutionary processes on a grand scale. The limited interactions between dark matter and ordinary matter lead to profound implications. They challenge our current understanding of physics and suggest enigmatic properties of dark matter that remain to be fully unraveled. As researchers continue to explore these interactions, they blaze trails toward uncovering one of the universe's most compelling mysteries, potentially reshaping our view of reality. Astrophysicists refer to dark matter as invisible because it does not emit, absorb, or reflect light, making it undetectable through traditional telescopes. Instead, it interacts with ordinary matter and radiation only via gravity. This elusive nature is one of the primary reasons why dark matter remains a mystery. We can see its gravitational effects on galaxies and galaxy clusters, but we cannot observe the substance itself. Think of it like trying to detect the presence of a ghost in a room. You can't see it, but when the curtains flutter or an object moves, you know something is there. The challenges posed by this invisibility are significant for scientists. For one, it complicates the process of identifying the particles that make up dark matter. Since these particles do not interact with light or other forms of electromagnetic radiation, experiments designed to detect dark matter directly often have to be set up far underground or shielded from cosmic rays, adding layers of complexity to the research. Moreover, the inability to observe dark matter directly means that astrophysicists must rely heavily on indirect evidence, drawing conclusions based on the gravitational influences it appears to exert on visible matter. Moreover, the search for dark matter involves innovative techniques and technologies. Some researchers aim to create high-energy collisions in particle accelerators, hoping to generate dark matter particles that can be captured and studied. Others are looking into delicate detectors that can sense the minuscule effects of dark matter interactions. Each approach brings with it a series of uncertainties and requires careful interpretation of results, which often leads to debates within the scientific community about the nature of these enigmatic particles. Despite these challenges, the pursuit of understanding dark matter is a driving force in modern astrophysics. The quest not only deepens our understanding of the universe, but also raises profound questions about the very fabric of reality. As observations continue to accumulate and new technologies emerge, the hope is that one day, dark matter will no longer remain a ghostly presence but will be revealed as a fundamental component of the cosmos. Dark matter, the mysterious substance that makes up about 27% of the universe, plays a crucial role in shaping its fate. Unlike normal matter, dark matter does not emit, absorb, or reflect light. Instead, it interacts with regular matter through gravity. This gravitational influence is essential for the structure and evolution of the cosmos. As galaxies form and evolve, dark matter serves as a framework that holds them together. As we look to the future, dark matter impacts the potential scenarios for the ultimate fate of the universe. One possibility is the Big Freeze, where the universe continues to expand indefinitely. In this scenario, galaxies drift apart, stars burn out, and the cosmos becomes cold and dark. Dark matter, contributing to the expansion rate, could help determine how quickly this spread occurs. If dark energy, another mysterious force, continues to drive the universe's expansion faster, dark matter's gravitational forces may either resist this expansion or play an invaluable role in how structure persists over time. Alternatively, if certain properties of dark matter were to change, it could lead to different outcomes. For instance, if dark matter were to behave differently under certain conditions, it might enhance gravitational clumping, potentially leading to a universe where galaxies are pulled back together. This could result in a big crunch, where the expansion reverses and everything collapses back into a singular point. Although this scenario currently seems unlikely, ongoing research into dark matter could change our understanding about its properties and interactions. Ultimately, the fate of our universe is linked to its unseen components. As we delve deeper into the mysteries of dark matter and its effects, we might uncover new insights that could reshape our understanding of cosmic destiny. Each discovery about dark matter offers an opportunity to appreciate the intricate, unseen forces that govern our cosmos, piquing our curiosity about the future of everything we see and beyond. Dark matter is one of the most intriguing concepts in modern astrophysics, as it serves as a key to understanding several unexplained phenomena in the universe. One of the most prominent mysteries is the rotation rates of galaxies. When scientists observe how fast galaxies spin, they notice something puzzling. The outer regions of galaxies rotate much faster than would be expected based solely on the amount of visible matter. This discrepancy suggests that there is an unseen mass, dark matter, providing the gravitational pull necessary to keep these stars in their fast orbits. Another enigmatic phenomenon linked to dark matter is gravitational lensing. As light travels across the cosmos, it can be bent by the gravitational field of massive objects like galaxies or clusters of galaxies. This bending of light can create distorted or multiplied images of distant celestial bodies. Observations reveal that the amount of lensing exceeds what we would expect from the visible matter alone. Dark matter, spread throughout and beyond these massive structures, is the explanation for this unexpected bending, indicating vast reservoirs of unseen mass. Additionally, dark matter plays a crucial role in the formation of large-scale structures in the universe. The cosmic web of galaxies, clusters, and voids seems too intricate to have formed purely from visible matter. Computer simulations that include dark matter reveal that its presence allows for the gravitational scaffolding needed to form these large structures over billions of years. Without dark matter influencing the formation process, the universe as we know it would look vastly different, with fewer galaxies clustered together. Finally, the cosmic microwave background radiation, the afterglow of the Big Bang, provides another piece of evidence for dark matter. Tiny fluctuations in temperature observed in this ancient radiation can be attributed to the gravitational effects of dark matter. These fluctuations reflect the density variations in the early universe, where dark matter played a critical role in shaping the cosmos from its infancy. All these phenomena highlight the fundamental importance of dark matter in our understanding of the universe, leaving many questions still ripe for exploration. The existence of dark matter has captivated astronomers and physicists for decades, primarily due to compelling evidence that suggests its presence throughout the universe. One of the most striking pieces of evidence comes from the behavior of galaxies. When astronomers measure the rotation speeds of galaxies, they observe something perplexing. The outer regions of galaxies rotate much faster than expected. According to the laws of gravity, if only visible matter were present, the outer stars should be moving more slowly. This discrepancy hints at an unseen mass, dark matter, exerting gravitational influence. Another key piece of evidence arises from the study of galaxy clusters. When scientists observe these massive formations, the visible mass, made up of the stars and gas, only accounts for a fraction of the total mass needed to hold the cluster together. The gravitational effects, such as the way galaxies within the cluster move and the bending of light from distant objects, a phenomenon known as gravitational lensing, indicate that there is much more mass than we can see. This unseen mass is attributed to dark matter, which plays a crucial role in the formation and structure of the universe. Cosmic microwave background radiation provides further support for dark matter. This radiation is a relic from the early universe, and its study reveals fluctuations in temperature that correspond to density variations in the early cosmos. The pattern of these fluctuations suggests a universe dominated by dark matter, which influenced how regular matter clumped together after the Big Bang. The data collected from space observatories like the Wilkinson Microwave Anisotropy Probe solidifies our understanding of dark matter's role in shaping the early universe. Together, these pieces of evidence form a compelling case for dark matter's existence. While we may not be able to directly observe dark matter, its influence is felt everywhere, from the intricate dance of galaxies to the structure of cosmic radiation. As we continue to explore the universe, dark matter remains one of the most intriguing mysteries, inviting scientists to unravel its secrets and understand our cosmic neighborhood more fully. Black holes and dark matter are both fascinating components of the universe, each playing crucial roles in cosmic evolution. Black holes, regions in space where gravity is so strong that not even light can escape, are formed from the remnants of massive stars that have collapsed. Dark matter, on the other hand, is an invisible substance that makes up about 27% of the universe's mass. It does not emit, absorb, or reflect light, making it difficult to detect directly. However, its presence is inferred from gravitational effects on visible matter, such as stars and galaxies. Research shows that black holes and dark matter interact primarily through gravity. As galaxies evolve, dark matter helps to shape their formation and structure, creating gravitational wells that attract normal matter and eventually form stars. These black holes, especially supermassive ones found at the centers of galaxies, influence their surrounding environment. They can affect star formation rates and gas dynamics, which are crucial for galactic evolution. Interestingly, black holes might also influence the distribution of dark matter within galaxies. As black holes consume material, they emit energy in the form of radiation, altering the dynamics of the surrounding dark matter. This interaction could lead to different configurations of dark matter in galaxies, contributing to the variety we observe across the universe. The interplay between black holes and dark matter presents a more complex picture of cosmic evolution than scientists once thought. By studying how these entities interact, astronomers gain deeper insights into the history and future of our universe, revealing that the cosmos is not just filled with stars and planets, but intricately woven with unseen forces and mysterious phenomena. As we advance our understanding, the relationship between these two cosmic powers will undoubtedly yield more surprises in the grand tapestry of our universe's history. Gamma-ray bursts are intense flashes of gamma rays, the most energetic form of light in the universe. They typically last from a few milliseconds to several minutes and are thought to be caused by catastrophic cosmic events such as the explosion of massive stars in supernova or the collision of neutron stars. These bursts can release as much energy in a few seconds as the sun will emit over its entire 10 billion-year lifetime. One of the reasons gamma-ray bursts are considered terrifying is their sheer power. A single burst can emit more energy than the sun will produce throughout its entire existence. If a gamma-ray burst were to occur relatively close to Earth, say within a few thousand light-years, the gamma rays could potentially deplete the ozone layer, exposing our planet to harmful ultraviolet radiation. This could lead to devastating consequences for life on Earth. Moreover, they occur without warning, appearing suddenly and unpredictably. Scientists have detected these bursts from billions of light-years away, showcasing their ability to travel vast distances through space. Each new observation adds layers to our understanding, but the unpredictability of these events keeps the scientific community on high alert regarding their potential impact on Earth. While gamma-ray bursts are terrifying due to their potential effects, they also serve as a reminder of the dynamic and violent nature of the universe. They provide scientists with invaluable information about the life cycles of stars and the conditions surrounding stellar explosions. Each discovery helps uncover the secrets of the cosmos, ensuring that our understanding continues to evolve alongside the mysteries of the universe. To understand the remarkable bursts of energy in the universe, we must look at phenomena such as supernovae and gamma-ray bursts. At their core, these events are rooted in the life cycles of stars. Stars, like our own Sun, spend most of their lives converting hydrogen into helium through nuclear fusion, releasing energy in the process. But when a star exhausts its fuel, dramatic changes occur that lead to stunning explosions. In the case of a supernova, when a massive star has burned through its core's nuclear fuel, it can no longer support its own weight. The core collapses under immense gravity, causing a rebound effect that sends shockwaves outward. This catastrophic explosion can outshine an entire galaxy for a brief period, releasing more energy than the Sun will emit in its entire lifetime. In this moment, elements are forged and expelled into space, seeding the universe with the building blocks for new stars and planets. Gamma-ray bursts, on the other hand, represent some of the most energetic events observed in the universe. These bursts can occur when a massive star collapses into a black hole or when two neutron stars merge. They release beams of gamma rays that can last from milliseconds to several minutes. What's fascinating is that while only a tiny fraction of the energy is cast in our direction, that energy far exceeds the luminosity of an entire galaxy, making them incredibly powerful events. Both phenomena, the supernova and gamma-ray burst, highlight the fascinating interplay of gravity, energy, and stellar evolution. They remind us of the dynamic and ever-changing nature of the cosmos, where powerful bursts of energy can forge the very elements that make up our world and shape the universe as we know it. These immense bursts are not just spectacular fireworks in the night sky. They are vital processes that drive the evolution of the universe itself. Gamma-ray bursts are among the most powerful explosions in the universe, often originating from massive stars collapsing into black holes or from the merger of neutron stars. These events are quite rare on a universal scale. On average, astronomers estimate that gamma-ray bursts occur about once every 100 years in a galaxy like ours, the Milky Way. That means while they are frequent throughout the universe, they are relatively uncommon in any single galaxy. Now, considering the vastness of space, the likelihood of a gamma-ray burst directly affecting Earth is exceedingly low. Our planet is shielded by an atmosphere and a magnetic field, which provide protection against many forms of cosmic radiation. Even if a gamma-ray burst were to occur in our vicinity, say within a few thousand light years, it would need to be oriented just right to have any significant impact on our atmosphere. Thankfully, there have been no gamma-ray bursts close enough in our galaxy that posed any real threat. As we look into the cosmic scales of time and space, it's fascinating to realize that the energy released by a gamma-ray burst can outshine entire galaxies for brief moments, lasting only seconds to a few minutes. These bursts emit intense bursts of gamma radiation and can sometimes be seen from vast distances. Their power, while breathtaking, is generally too far removed to worry us here on Earth. In conclusion, while gamma-ray bursts are fascinating phenomena that deserve our interest, they pose little danger to our planet. The universe may be brimming with energy and excitement, but for now, we can observe these bursts as a reminder of the dynamic and ever-changing cosmos, knowing that Earth remains in a relatively safe spot in this grand celestial drama. Gamma-ray bursts are among the most powerful explosions in the universe, releasing immense amounts of energy within a very short time. To put this in perspective, a single gamma-ray burst can emit as much energy in a few seconds as the Sun will produce over its entire 10 billion-year lifetime. If such an event were to occur close to Earth, it could indeed have catastrophic effects on a planetary scale. One of the primary concerns with a nearby gamma-ray burst is the impact on our atmosphere. These bursts emit high-energy gamma rays which can strip away the ozone layer, the protective shield that absorbs the majority of the Sun's harmful ultraviolet radiation. Without this layer, increased levels of UV radiation would reach the surface, leading to a surge in skin cancers, damaging effects on ecosystems, and disruptions in food chains. The consequences could extend beyond individual health issues, affecting agriculture and the environment on a global scale. Moreover, gamma-ray bursts could initiate a cascade of effects in our climate. The intense radiation could lead to chemical reactions in the atmosphere that might cool the planet temporarily due to particles being expelled into the stratosphere, blocking sunlight. This phenomenon could trigger dramatic climate shifts, causing temperature drops and altering weather patterns. Such changes would challenge the delicate balance of our ecosystems, making survival increasingly difficult for many species. While the probability of a gamma-ray burst occurring close enough to Earth to cause such catastrophic effects is exceedingly low, these events remind us of the vast universe we inhabit. They serve as a stark example of the potential dangers lurking beyond our atmosphere, emphasizing the importance of understanding cosmic phenomena and their effects on our planet. The study of gamma-ray bursts not only fascinates astronomers, but also provides valuable insights into the workings of our universe and the fragility of life on Earth. Gamma-ray bursts are among the most powerful explosions in the universe, unleashing energy that can outshine entire galaxies in mere moments. Although these cosmic events are incredibly rare, they pose a potential threat to life on Earth, primarily due to their intense radiation. When a gamma-ray burst occurs within a distance of approximately 6,000 light-years, the effects could be catastrophic for our planet. The high-energy gamma rays could strip away the ozone layer, a critical shield that protects us from harmful ultraviolet radiation from the sun. Moreover, if a gamma-ray burst were to occur nearby, it could lead to severe environmental consequences. With the ozone layer compromised, increased levels of ultraviolet radiation would penetrate the Earth's atmosphere, leading to harmful impacts on living organisms. This could cause a dramatic rise in skin cancer cases in humans, disrupt ecosystems, and threaten various species, particularly those that are sensitive to radiation. Interestingly, scientists believe that such bursts occur due to the collapse of massive stars or the merger of neutron stars. These events create jets of gamma rays that shoot out into space, and if aligned with Earth, the impact could be devastating. While the probability of a gamma-ray burst directly affecting our planet is low, the sheer energy involved leaves us pondering the vulnerability of life in the cosmos. Despite the potential risks, it's important to note that life on Earth has endured many cosmic events over the eons. Our planet has weathered asteroid impacts, supernova explosions, and even climate changes, while gamma-ray bursts represent a fascinating and alarming aspect of our universe. They also remind us of the resilience of life and the intricate balance that exists within cosmic forces. Gamma-ray bursts, or GRBs, are among the most energetic events in the universe. These bursts of gamma rays signify some of the most powerful explosions known, and they primarily come in two distinct types: long-duration and short-duration gamma-ray bursts. The classification is based mainly on their duration, with long bursts lasting more than 2 seconds and short ones lasting less than 2 seconds. Long-duration gamma-ray bursts often result from the collapse of massive stars. When a large star exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. This collapse can lead to the formation of a black hole, unleashing a colossal amount of energy that is observed as a GRB. A notable example is the burst designated GRB 980425, which likely originated from a supernova in a galaxy far from our own, illustrating the connection between GRBs and stellar evolution. On the other hand, short-duration gamma-ray bursts are believed to come from the merger of compact objects, like two neutron stars or a neutron star and a black hole. These events create gravitational waves in addition to bursts of gamma rays. One remarkable example is GRB 170817, which was detected in August 2017. This event was particularly groundbreaking as it was observed simultaneously with gravitational waves, providing invaluable insights into the nature of such cosmic collisions and marking a significant milestone in multi-messenger astronomy. Both types of gamma-ray bursts serve as magnificent cosmic beacons, allowing astronomers to study the fundamental processes of the universe. Their immense energy and the distances they can span mean that GRBs not only deepen our understanding of stellar life cycles and cosmic events, but also challenge our grasp of the universe's structure and evolution. Through continued observation and study, these bursts remain a vital area of research, revealing secrets about the universe that still captivate scientists and curious minds alike. Gamma-ray bursts, the most intense and energetic explosions known in the universe, have captured the attention of scientists since their discovery in the late 20th century. Observations began with military satellites originally designed to monitor nuclear tests. They detected these high-energy radiation bursts from far-off galaxies, and the sheer power of these events was astonishing. In those early days, the bursts felt almost mythic, portents of cosmic violence that defied much of what we understood about celestial mechanics. As telescopes improved and technology advanced, scientists learned to pinpoint the origins of these bursts with greater accuracy. Instruments like the Swift satellite, launched in 2004, played a pivotal role in detecting gamma-ray bursts within seconds of their occurrence. Swift allows astronomers to not only measure the gamma rays, but also observe the afterglow in other wavelengths, such as X-rays and visible light. This multi-wavelength approach has been crucial in unraveling the life cycle of a gamma-ray burst, revealing that they often result from massive star explosions or the collisions of dense neutron stars. Through extensive study, researchers discovered that gamma-ray bursts are typically mere seconds to a few minutes long, with energy output dazzlingly more powerful than billions of stars combined. This means that if a gamma-ray burst occurred close to Earth, even within 2,000 light-years, it could significantly affect our planet's atmosphere and potentially disrupt life as we know it. The fearsome reputation of these bursts essentially stems from their colossal energy release, which can trigger atmospheric ionization and affect the climate. Yet the story of gamma-ray bursts is not solely one of destruction and fear. They also serve as catalysts for learning about the universe's most fundamental processes. By studying these explosions, scientists are piecing together the mysteries of star formation, supernovae, and the formation of black holes. Each gamma-ray burst not only illuminates the cosmic distance between us and the remnants of the early universe, but also reshapes our understanding of the forces that govern the cosmos, unveiling the intricate dance of creation and annihilation that defines our existence. Gamma-ray bursts are incredibly intense explosions in distant galaxies, and they have sparked a lively discussion within the scientific community about their origins. These bursts release more energy in just a few seconds than our sun will emit throughout its entire life, which has left researchers in awe and eager to understand what triggers such spectacular phenomena. The debate centers mainly around two leading theories: the collapse of massive stars and the merger of neutron stars. Within the first theory, astronomers believe that some gamma-ray bursts are caused by the core collapse of massive stars. These stars, often more than 20 times the mass of our Sun, burn their nuclear fuel incredibly quickly. When they exhaust this fuel, they can no longer support themselves against gravitational forces and collapse, resulting in a supernova. In some cases, the collapsing core leads to the formation of a black hole, while jets of energy fire outwards at near-light speed. If these jets are pointed toward Earth, they produce a gamma-ray burst that we might detect across vast distances. The second theory involves the merger of compact objects, specifically neutron stars. Neutron stars are remnants of supernova explosions, and they are incredibly dense. When two neutron stars orbit each other closely, they can eventually spiral in and collide. This collision creates gravitational waves and a burst of gamma rays. Recent observations have provided strong support for this scenario, especially following the discovery of gravitational waves from such mergers, confirming the connection to gamma-ray bursts. Despite advancements in our understanding, the debate continues. Researchers are still working to determine the rates at which these events occur, and whether other previously unconsidered processes might also contribute to gamma-ray bursts. As telescopes and detection methods improve, the quest to fully understand these cosmic explosions remains a captivating frontier in astrophysics, promising new revelations about the universe and its most powerful phenomena. The discovery of gamma-ray bursts, or GRBs, has significantly shifted our understanding of stellar evolution and the life cycles of massive stars. These powerful explosions occur when a massive star runs out of fuel and undergoes a catastrophic collapse. These bursts represent the end stages of a star's life, showcasing a dramatic transformation that was previously not well understood. Before the identification of GRBs, scientists primarily studied supernovae as the endpoint of stellar evolution for heavy stars. But GRBs have opened up a new chapter in this story. Gamma-ray bursts are not only extreme events, but also provide a glimpse into the core physics of stellar collapse. When a massive star collapses, it can emit enormous amounts of energy in the form of gamma rays, which are the most energetic form of electromagnetic radiation. This process is often linked to the formation of a black hole or a neutron star. The energy released during a GRB can be equivalent to that produced by our Sun over its entire lifetime, but emitted in just a few seconds. This tells us that the internal mechanisms of these stellar processes are extraordinarily complex and energetic. Moreover, the discovery of GRBs has implications beyond our own galaxy. We now know these explosions can occur at vast distances and are observable across the universe. By studying these distant bursts, astronomers can learn about the conditions and processes of star formation and evolution in different cosmic epochs. For instance, some GRBs have provided insights into star formation rates in the early universe, shedding light on how stars and galaxies evolved after the Big Bang. Gamma-ray bursts have transformed our picture of stellar evolution, revealing that the fates of massive stars are more diverse and intense than previously thought. They highlight the interconnectedness of cosmic events and the continuous cycle of birth and death in the universe. The study of GRBs not only helps us understand the life stories of stars, but also paints a broader picture of the universe's history and the remarkable processes that shape it. A rogue planet is a celestial body that wanders through space without being tethered to any star. Unlike typical planets that orbit a sun, these planets have either been ejected from their original solar systems or formed in isolation in the vastness of the cosmos. Estimates suggest there could be more rogue planets in our galaxy than stars, creating an intriguing idea that the universe is filled with these free-floating worlds. What makes rogue planets particularly fascinating is their mysterious nature. Without a sun to provide warmth and light, these planets can become extremely cold and dark. They may not have the same kind of geological or atmospheric activity that planets in a solar system experience, which adds to an aura of isolation and the unknown. Scientists often wonder about the conditions on these planets. Could they harbor life in some unexpected form? Or are they entirely barren, devoid of warmth and atmosphere? Rogue planets also challenge our understanding of planetary formation and dynamics. The traditional view posits that planets form in stable orbits around stars. However, the existence of rogue planets suggests that the processes of planet formation and interaction are far more complex. For instance, these planets could have once belonged to a larger solar system, only to be flung out by gravitational encounters, making us rethink what conditions foster the birth of a planet. The very idea of wandering worlds taps into a deep-rooted sense of mystery and exploration. With each discovery of rogue planets, we are reminded of the unpredictable dance of cosmic forces at play in the universe. Every rogue planet we identify invites us to ponder not just its story, but also the stories of countless more hidden in the ocean of stars. Rogue planets, those elusive wanderers drifting alone through the vastness of the galaxy, are both fascinating and challenging to detect. Unlike stars or planets that orbit a star, rogue planets do not emit their own light. Instead, scientists often rely on indirect methods to spot these elusive celestial bodies. One primary technique is gravitational microlensing. Gravitational microlensing occurs when a massive object, like a rogue planet, passes in front of a distant star. The intense gravitational field of the rogue planet can bend the light coming from that star, creating a temporary increase in brightness. Scientists carefully monitor many stars in our galaxy, looking for fleeting changes in light that might indicate a rogue planet's presence. This technique can even detect planets that are located several thousand light-years away from us. Another approach incorporates infrared observations. Rogue planets, despite not being tied to a star, can still emit some heat left over from their formation. Scientists use powerful infrared telescopes to locate these warm objects in the darker regions of space. They can identify these planets by measuring the infrared radiation they emit, helping to confirm their existence even without the aid of a parent star. Moreover, advancements in observational technology have led to the discovery of more rogue planets in recent years. With the ability to analyze large datasets from surveys, astronomers can enhance their search for these lonely travelers. Each rogue planet found not only increases our understanding of the diversity of planetary systems, but also raises intriguing questions about how these worlds came to wander alone, hinting at the dynamic nature of our universe. Rogue planets are fascinating celestial bodies that drift through space without being tethered to any star. These planets might have formed in the traditional way, circling their parent stars, but for some reason, they were ejected into the vast, dark expanse of the cosmos. This phenomenon raises compelling questions about the conditions that might support life beyond our solar system. The implications of rogue planets for the search for extraterrestrial life are significant. Firstly, these planets could potentially harbor subsurface oceans or other forms of liquid water protected beneath thick ice layers. If such conditions exist, they would create an environment where microbial life could survive, even in the absence of a nearby star. Rogue planets could act as isolated worlds, preserving the potential for life in a way that is independent of stellar influence. Moreover, rogue planets may also provide clues about the cosmic evolution of life. If these planets were once associated with a vibrant, life-supporting system before being cast out, they may carry the remnants of their origins. This suggests that life could be more adaptable and resilient than we once believed, thriving in diverse and extreme environments, and evolving on planets that wander far from the familiar warmth of stars. Finally, the discovery of rogue planets expands our understanding of the distribution of habitable environments in the universe. Each new rogue planet we identify might challenge our preconceived notions of where life could exist. This means that the search for extraterrestrial life may not be limited to those areas typically associated with stars, but could extend to these wandering worlds, letting our imagination and scientific endeavors reach further into the cosmos than we ever thought possible. Imagine a planet drifting through space, untethered by any star. This is what we call a rogue planet, and while they may seem distant and isolated, their journey across the cosmos can have profound implications for the stability of our solar system. Over time, a rogue planet could enter our solar system's vicinity, potentially disrupting the delicate balance of gravitational forces that govern the orbits of the planets. One significant threat posed by a rogue planet stems from its gravitational influence. As it approaches, it could alter the orbits of objects in the outer solar system, notably the icy bodies of the Kuiper Belt and the Oort cloud. This shift could send long dormant comets hurtling toward the inner solar system, increasing the risk of collision with Earth or other planets. Such impacts could lead to catastrophic consequences, including climate disruption or mass extinction events. Moreover, the sheer mass of a rogue planet can have unforeseen effects on the planets closest to it, particularly the gas giants like Jupiter and Saturn. Their powerful gravitational fields could either capture the rogue or deflect it away, but not without consequences. The interaction might provoke changes in the orbits of our own planets, possibly leading to a chaotic reshuffling of celestial bodies over millions of years. Audiences might wonder, could rogue planets be a common occurrence? Absolutely. Scientists estimate that rogue planets could outnumber stars in our galaxy. So while they may pose a long-term threat, they also offer a glimpse into the dynamic and unpredictable nature of the universe. As we continue to explore the cosmos, understanding these wandering giants becomes essential in safeguarding our own celestial neighborhood. The fascinating world of rogue planets presents a captivating mystery in the broader field of astronomy. Rogue planets, which are worlds that drift through space without being bound to any star, come into existence through several theories that hint at the complex dynamics of planetary formation and evolution. One prominent hypothesis is that some rogue planets formed in the early stages of stellar systems, much like regular planets. They could have begun their journey in a solar neighborhood, forming around a star, and over time could be ejected into interstellar space due to gravitational interactions. Another intriguing scenario suggests that rogue planets could arise from catastrophic events within their parent star systems. For instance, during the chaotic formation phases, interactions between multiple forming planets can lead to ejections. Imagine a cluster of young gas giants, their orbits destabilizing as they interact with one another, leading to a scenario where one or more planets are flung away into the void, never to return. Such violent events could easily account for a significant portion of the rogue planets we observe today. Additionally, There is the theory that some rogue planets might not always be solitary beginners. Instead, these planets could begin their lives as moons orbiting a larger gas giant, only to be expelled from their host when gravitational forces shift due to various reasons, such as the migration of the larger planet within its system. This process could lead to a moon transforming into a rogue planet, wandering through interstellar space, devoid of any stellar light. Considering the vastness of our universe, the potential for diverse origins of rogue planets only adds to their allure. Each drifting planet carries with it a story of dynamics, chaos, and survival, challenging our understanding of how planetary systems operate and evolve. With ongoing advancements in astronomical observation, the study of these enigmatic worlds continues to intrigue scientists, revealing more about the complex tapestry of the cosmos. Rogue planets, those mysterious wanderers that drift through the cosmos without a parent star, have a fascinating relationship with the stars they encounter. As these planets move through space, they can come surprisingly close to stars, leading to a range of interactions. When a rogue planet nears a star, the immense gravitational forces at play begin to affect both bodies. The planet can be drawn into the star's gravitational pull, changing its trajectory dramatically, or alternatively, the star's gravitational influence might alter the planet's course. If a rogue planet is captured by a star's gravity, it can become part of that star's system, joining the ranks of other planets. This introduction can have serious consequences for existing planet formation. The gravitational tug of the new arrival could lead to instabilities, causing shifts in the orbits of already residing planets, potentially destabilizing their paths. This might culminate in collisions or ejections of other objects within the system, creating a chaotic dance of celestial bodies. Conversely, if the rogue planet passes close enough to a star without being captured, it can still impart significant effects. The interaction might lead to a transfer of energy, especially if the planets have similar masses. This exchange can result in tidal forces that may cause noticeable changes in the star's outer layers. For stars that have inhabited inner planetary systems, such encounters could lead to alterations that make those environments hostile or create new conditions for life. Ultimately, the interaction of rogue planets with stars is a testament to the unpredictable nature of the universe. Each encounter tells a story of orbital dynamics, influencing the evolution of star systems and reminding us of the diversity and complexity of cosmic relationships. Each rogue planet's journey adds another layer to our understanding of the cosmos, showcasing the intricate dance of creation and destruction inherent to the universe. Rogue planets are truly fascinating celestial bodies. Unlike traditional planets that orbit a star, rogue planets wander the cosmos freely, untethered by any star's gravitational pull. This independence gives them a unique trait. They exist in isolation, drifting through space. It's estimated that there could be billions of these orphaned worlds in our galaxy alone. One of the most striking characteristics of rogue planets is their formation. While many planets form within a protoplanetary disk around a star, rogue planets might originate in similar ways, but are later ejected during violent gravitational encounters, such as collisions with other large bodies. This tumultuous journey sets them apart, as they can emerge with varied sizes and compositions, often resembling anything from gas giants to icy worlds. Temperature is another remarkable feature. Since rogue planets do not receive heat from a nearby star, many of them are incredibly cold. They can reach temperatures that are just a few degrees above absolute zero, which makes them daunting environments. However, some may retain heat generated from their formation or from radioactive decay, potentially allowing for a unique set of chemical processes and conditions. An intriguing aspect of rogue planets is their potential for hosting life. While this may sound unlikely given their cold and dark surroundings, some scientists speculate that if these worlds possess subsurface oceans similar to those believed to exist on moons in our solar system, they could maintain a suitable environment for life. This leads to the captivating idea that life could exist in places we traditionally overlook, wandering as freely as the rogue planets themselves. The potential discovery of rogue planets, those wandering celestial bodies that drift through space without being bound to any star, has raised significant concern among astronomers. These planets defy conventional understanding. While most planets, like those in our solar system, orbit stars, rogue planets lack such anchors. Their existence suggests that the universe might harbor far more planets than previously thought, many of which are isolated and could, in theory, harbor life in hidden environments. One of the alarming implications of rogue planets is their unpredictable nature. Since they do not have a star's gravitational influence, their paths can be erratic. They can wander through galaxies, potentially colliding with other celestial bodies or disrupting the orbits of nearby stars. This unpredictability creates challenges for celestial navigation and studying planetary systems. It raises questions about the stability of systems we are currently observing, where a rogue planet might intrude unexpectedly. Moreover, rogue planets might possess environments that are entirely different from what we know. They could retain heat from their formation or have internal geologic processes that sustain subsurface oceans. The prospect of such hidden worlds challenges our definitions of habitability and raises the tantalizing possibility that they could host some form of extraterrestrial life. However, the vast distances and lack of illumination make them incredibly difficult to study. Finally, the existence of rogue planets invites us to rethink our understanding of planetary formation and evolution. How do these planets come to be? Are they ejected from their star systems due to gravitational disturbances, or do they form independently in the vastness of space? These questions drive researchers to explore and redefine what we know about the universe, reminding us that in our quest to understand the cosmos, new discoveries can often lead to more mysteries. Rogue planets are fascinating celestial bodies that drift through space without being tethered to a star. Recent research suggests that there could be billions of these worlds wandering through our galaxy, far away from their original planetary systems. This realization prompts a profound shift in how we understand the formation and evolution of planetary systems throughout the universe. Firstly, the existence of rogue planets challenges the traditional view of planetary system stability. Many models of planet formation assume that planets are formed and remain bound to their stars, but rogue planets introduce the idea that some may be ejected from their systems due to gravitational interactions. This opens up new questions about the processes that lead to planetary ejections and the dynamics of early planetary system formation. It suggests that our solar system, like many others, may have once harbored more planets than we currently see. Furthermore, rogue planets could provide insights into the possibilities for life beyond our solar system. Since they are not reliant on a star for warmth, these planets might possess internal heat generated by radioactive decay. This raises intriguing possibilities for subsurface oceans or even ecosystems thriving far from sunlight. As we continue to explore these worlds, we may find that life could exist in environments we had previously deemed inhospitable. Lastly, the discovery of rogue planets emphasizes the need for updated models of galactic evolution. With the sheer number of these planets potentially outnumbering those in stable orbits, they could significantly influence cosmic events, such as the interactions with other celestial bodies. Understanding the role of rogue planets in the universe enriches our knowledge of cosmic phenomena and helps astronomers refine their theories about the formation, life cycles, and interactions of planetary systems across the vast cosmos. Cosmic voids are immense regions of space that contain very few galaxies, resulting in vast expanses that seem almost empty when viewed against the backdrop of the more densely populated areas of the universe. To understand them more deeply, think of the universe as a vast cosmic web, where galaxies are interconnected by filaments of dark matter and gas, creating clusters and superclusters. The voids represent the spaces in between these structures, often measuring tens to hundreds of millions of light-years across. The unsettling nature of cosmic voids comes from their magnitude and the questions they raise about the composition and fate of the universe. These regions can be so expansive that they might make one ponder the implications of nothingness on such grand scales. Unlike a vacuum we might experience on Earth, cosmic voids challenge our perceptions of reality by existing as large, nearly empty spaces, making up about 80% of the universe's volume. This notion becomes even more intriguing when we consider the invisible components that fill the universe, such as dark energy and dark matter, which we cannot directly observe. Further adding to the intrigue of cosmic voids is their role in the universe's evolution. They influence galactic formation and distribution, impacting how galaxies cluster together and how they interact. The presence of a void can affect the gravitational influences that shape neighboring galaxies, leading to a complex dance that illustrates the interconnected nature of cosmic structures. While voids might appear as mere emptiness, they are anything but simple. They deepen our understanding of cosmic dynamics and challenge our ideas about what constitutes the universe as a whole. The mysteries surrounding cosmic voids keep scientists and astrophysicists engaged, as each discovery provides a new piece in the ever-expanding puzzle of our universe's structure and history. Cosmic voids are vast, nearly empty regions of space that make up a significant part of the universe's large-scale structure. They are formed through intricate gravitational processes over billions of years. Initially, the universe was a hot, dense soup of particles. As it expanded, slight fluctuations in density allowed matter to clump together, forming galaxies and clusters. The areas where less matter congregated, however, evolved into these relatively empty voids. These voids can span tens of millions of light-years across and contain very few galaxies compared to denser regions. Their formation is linked to the growth of cosmic structures. As gravity pulls matter into filaments, long strands of galaxies and galaxy clusters, what remains in between are these voids. This process illustrates the universe's dynamic nature, where dark matter plays a crucial role as it guides the formation and movement of visible galaxies and their clusters. Understanding cosmic voids is essential for cosmologists because they offer insights into the evolution of the universe. They help scientists analyze how matter is distributed on a large scale and provide clues about the mysterious dark energy that is driving the universe's accelerated expansion. Interestingly, the properties of these voids can reveal how space itself is structured and how galaxies interact with one another over cosmic time. Moreover, the existence of voids highlights the universe's unexpected complexities. Researchers have discovered that voids are not just empty spaces. They can influence the behavior of galaxies and cosmic rays, contributing to a broader understanding of cosmic phenomena. By studying cosmic voids, scientists unlock secrets about our universe's history, its present state, and its ever-evolving future. Cosmic voids are vast, largely empty spaces that make up about 80% of the universe's volume. In contrast, densely populated regions, often known as galaxy clusters, are teeming with galaxies, stars, and other celestial phenomena. The gulf between these two regions illustrates the universe's intricate structure and continuous evolution. The contrast in density is striking. In densely populated areas, millions of galaxies can be found within a relatively small area, bound together by gravitational forces. These regions can sometimes reach temperatures in the millions of degrees, partly due to the dynamic interactions between galaxies and the presence of hot gas between them. This energetic environment gives rise to a variety of fascinating phenomena, including the formation of new stars and even supermassive black holes at the centers of galaxies. On the flip side, cosmic voids can be surprising in their emptiness. They can span upwards of 100 million light-years across, often containing only a few galaxies or none at all. The extremely low density of matter in these regions hints at the universe's grand design and is believed to play a critical role in guiding the overall structure. Researchers even suggest that these voids influence the motion of galaxies, creating an intriguing cosmic dance across vast distances. Moreover, the interactions between cosmic voids and densely populated areas contribute to the phenomenon of gravitational lensing. This effect occurs when light from distant galaxies bends around massive objects, providing vital insights into the distribution of dark matter. The stark dichotomy between voids and rich regions illustrates not just the complexity of cosmic architecture, but also our ongoing quest to understand the fundamental laws governing the universe itself. Cosmic voids are immense, almost empty regions of space that exist between galaxies. These vast expanses can stretch for hundreds of millions of light-years and contain very few galaxies, stars, or other matter. Despite their emptiness, cosmic voids play a significant role in the structure of the universe and can profoundly impact gravitational forces. One of the most intriguing consequences of these voids is how they influence the overall gravitational landscape of the universe. Since gravity is a force that attracts matter to itself, areas with less matter, like cosmic voids, exert a weaker gravitational pull. This means that where voids are present, the gravitational forces can be reduced. Consequently, galaxies and galaxy clusters are often found at the edges of these voids rather than in their centers. This arrangement leads to a fascinating cosmic structure, often likened to a web, where galaxies trace the filaments of denser regions, while voids delineate the emptiness in between. Furthermore, the presence of voids influences the motion of galaxies. As galaxies travel through the universe, they tend to be drawn toward regions of greater density, like the cluster formations that sit at the edges of these voids. This interplay of attraction creates a dynamic where the gravitational pull can create streams of galaxies moving toward one another while avoiding the empty spaces of voids. Over cosmic time, this movement helps shape the larger structures we observe in the universe today. Cosmic voids are not just empty spaces, they are active participants in the cosmic ballet of gravitational forces. By creating zones of lower gravity, they guide the motion of galaxies and help define the structure of the universe, giving us profound insights into how everything from small galaxy groups to massive clusters is connected within the vast tapestry of the cosmos. In the vast tapestry of the universe, scientists have uncovered intriguing structures known as cosmic voids. These expanses are massive regions of space that are remarkably empty, with far fewer galaxies than we observe elsewhere. To map these voids, researchers employ advanced techniques, often using data collected from large astronomical surveys. These surveys compile information from telescopes that scan the night sky, capturing light from distant galaxies across various wavelengths. One of the key methods involves analyzing the distribution of galaxies. By observing where galaxies cluster, scientists can identify areas of relative emptiness, those cosmic voids. The use of three-dimensional space visualization helps illuminate how these voids are situated within the cosmic web, an intricate arrangement of matter in the universe. This network consists of filaments of galaxies and clusters intertwined with vast voids that can stretch tens of millions of light-years across. Recent discoveries reveal that these voids play a significant role in shaping the universe. For instance, researchers found that voids can influence the motion of galaxies. As matter collapses into denser regions around these voids, the dynamics can accelerate the growth of structures in the universe. This has led scientists to reconsider how galaxies interact and evolve over cosmic time, providing insights into the life cycle of the universe itself. In addition to their role in the cosmic web, voids hold clues about the nature of dark energy and dark matter. Since these mysterious substances make up the majority of the universe, studying voids enables scientists to probe the fabric of reality itself. The more we learn about these emptinesses in space, the closer we come to understanding the overall architecture of the cosmos and the forces that govern its expansion. Each void is not merely empty, it is a fundamental piece of our universe's grand puzzle. Cosmic voids are vast regions of space that contain very few, if any, galaxies. These immense expanses make up about 80% of the universe and are critical in shaping its large-scale structure. Their influence on the fate of the universe has triggered fascinating discussions among cosmologists. One prominent theory posits that these voids impact the universe's expansion and its ultimate destiny. Since voids have low density, they create gravitational wells that affect the motion of galaxies and can potentially alter how quickly the universe expands. Another significant theory examines the role of cosmic voids in dark energy dynamics. Dark energy is the mysterious force driving the acceleration of the universe's expansion. Researchers suggest that the sheer presence of voids could influence the distribution of dark energy, affecting its perceived strength across different regions of space. In this sense, voids may act like lenses, amplifying or diminishing the impact of dark energy depending on their structure. Void dynamics also play a key role in galaxy formation and evolution, as they can influence the flow of matter. Galaxies often form at the edges of these voids, where the density is higher. This framework may suggest that the future of galaxy formation is deeply intertwined with the characteristics of the surrounding voids. Thus, as cosmic structures evolve, voids could dictate not only where stars and galaxies emerge, but also how they interact with one another over cosmic timescales. Ultimately, the theories surrounding cosmic voids remind us of the intricate tapestry of our universe. Each element, whether dense clusters of galaxies or vast empty expanses, contributes to a larger narrative about the universe's fate. As research continues, understanding these voids will not only give us deeper insight into cosmic evolution, but may also reveal more about fundamental questions regarding the nature of space, energy, and our place within this grand cosmos. Cosmic voids are vast, empty regions of space that contain very few galaxies and matter compared to other parts of the universe. These expansive voids may cover up to 80% of the universe's volume, yet they hold only around 20% of its mass. At first glance, such emptiness might seem benign or inconsequential. However, the existence and characteristics of these voids pose significant challenges to our understanding of dark energy, the mysterious force driving the universe's accelerated expansion. Dark energy is thought to be uniformly spread throughout space and exerts a repulsive force, pushing galaxies away from each other. When scientists study cosmic voids, they observe that the gravitational pull within these underdense areas behaves unexpectedly. Instead of seeing a uniform acceleration as dark energy would suggest, evidence shows that voids might actually decelerate the expansion of the universe locally. This results in a puzzling discrepancy that questions the simplistic application of dark energy across the entire cosmos. Furthermore, cosmic voids have impacts on galaxy formation and evolution. Within these massive empty spaces, the lack of gravitational pull means fewer galaxies can form. This contrasts sharply with the more densely populated areas known as galaxy clusters, where the interaction and accumulation of matter lead to a rich tapestry of cosmic structure. The stark differences in how galaxies are distributed and how they interact within these environments have prompted researchers to delve deeper into whether dark energy is indeed consistent across various cosmic scales. These findings push us to reconsider our models of the cosmos. If dark energy behaves differently in the presence of cosmic voids, it may lead to fascinating new insights about the universe's fabric and its ultimate fate. The study of cosmic voids thus serves as a vital piece of the puzzle in unraveling the complexities of dark energy, prompting scientists to broaden their understanding of the universe's expansion, structure, and the forces at play. This ongoing exploration highlights the need for a more nuanced understanding of dark energy in the grand narrative of cosmic evolution. Cosmic voids are vast, largely empty spaces in the universe, and they play a crucial role in the distribution of galaxies. These voids, which can span hundreds of millions of light-years across, serve as the backdrop for the cosmic web, a structure formed by dense filaments of galaxies and dark matter. Within this web, galaxies are not randomly scattered, but instead, they congregate along the edges of these voids, creating a fascinating pattern that reveals much about the evolution of the universe. The existence of cosmic voids helps to explain the large-scale structure of the universe. Galaxies are often found in clusters or groups along the filaments, while the voids themselves are sparsely populated. This arrangement allows astronomers to study how gravity influences galaxy formation and dispersal. As matter in the universe began to clump together, the gravitational pull of these denser regions attracted more matter, leading to the formation of galaxies and groups of galaxies, while empty spaces emerged as the leftover areas with minimal structure. Interestingly, the properties of cosmic voids also influence the environments of surrounding galaxies. For example, galaxies residing near the edges of voids can experience different conditions compared to those located within more densely populated areas. These differences can impact star formation rates and the chemical evolution of galaxies, demonstrating how their environments shape their development over billions of years. As scientists continue to explore cosmic voids, they reveal crucial insights into the nature of dark energy and the expansion of the universe. The distribution and size of voids can tell us not only about how galaxies cluster, but also about the overall dynamics of cosmic evolution. Understanding these vast, empty spaces helps us piece together the history of our universe and offers a glimpse into the fundamental forces that govern it. Cosmic voids are vast, empty spaces in the universe that make up about 80% of its total volume. These colossal regions contain very few galaxies, and their existence raises intriguing questions about the structure and formation of the universe. While they may seem barren, they play a significant role in shaping our cosmic landscape. Understanding these voids helps scientists unravel the mysteries of how matter is distributed and how the universe has evolved since the Big Bang. The interplay between cosmic voids and denser regions, like galaxy clusters, is a fundamental topic in cosmology. It turns out the gravitational interactions between these empty spaces and the surrounding galaxies affect the motion of galaxies and the overall architecture of large-scale structures. Voids act like gravitational wells, where less matter means lower gravitational pull, which influences the flow of galaxies over vast distances. This dynamic relationship reveals insights into dark matter and dark energy, two of the universe's most enigmatic components. Interestingly, the formation of voids is tied to the processes of cosmic evolution. In the early universe, small fluctuations in density led to the grouping of matter into galaxies and clusters, leaving behind areas devoid of significant matter. This evolution hints at the very fabric of reality and suggests a delicate balance between forces that shape everything we see or don't see. Quasars, short for quasi-stellar objects, are some of the most fascinating phenomena in the universe. These luminous entities are powered by supermassive black holes at the centers of distant galaxies. As galaxies evolve, gas and dust spiral into these black holes, heating up to extreme temperatures as they are accelerated by gravitational forces. This process releases vast amounts of energy, which can make a quasar outshine entire galaxies, shining brightly across billions of light-years of space. One of the reasons quasars elicit concern among astrophysicists is their potential role in the evolution of galaxies. As they expel powerful jets of particles into their surroundings, they influence the gas and dust in their host galaxies. This feedback mechanism can regulate star formation and affect the overall structure of galaxies. Understanding these processes is essential, yet it remains a complex puzzle that scientists continue to explore. Another source of trepidation arises from their immense distances and the implications of their brightness. The light we see from these objects has traveled for billions of years, which means we are observing them as they were in the early universe. Studying quasars offers a glimpse into the conditions that prevailed when the universe was only a fraction of its current age. Yet, this deep time connection also highlights the vastness and mystery of the cosmos. Realizing how little we understand about the early universe can indeed be daunting. Finally, there's an element of unpredictability associated with quasars. They can change in brightness over remarkably short timescales, raising questions about the activity surrounding the black holes they harbor. These fluctuations can lead scientists to rethink models of black hole physics and energy distribution. Thus, while quasars illuminate much about our universe, they also serve as a reminder of the limits of our knowledge, piquing both fear and intrigue as we confront the unknown. Quasars, or quasi-stellar objects, are some of the most fascinating and extreme phenomena in the universe, captivating astronomers since their discovery. At the core of a quasar lies a supermassive black hole that is actively consuming material, resulting in extraordinary emissions of energy. This process can create light that outshines all the surrounding stars in its host galaxy, making quasars some of the brightest objects in the cosmos. Interestingly, while they are incredibly luminous, they are also located billions of light-years away, giving us a glimpse into the early universe. One of the most puzzling aspects of quasars is their incredible variability. Observations have shown that the brightness of a quasar can change dramatically over short periods, sometimes within days or even hours. This variability suggests that the source of the quasar's light is relatively compact, likely within a region no larger than the size of our solar system. Such rapid changes in brightness challenge scientists' understanding of how matter behaves near a black hole, as the processes involved defy what we typically expect from celestial bodies. Moreover, quasars emit jets of particles traveling close to the speed of light. These jets can extend vast distances across the universe, often moving at incredible angles to the disk of material surrounding the black hole. The strength and speed of these jets remain subjects of intense research and debate. Understanding how these jets are formed and accelerated involves piecing together the complex interactions of magnetic fields and the inflow of matter, presenting a real challenge to physicists and astronomers alike. Finally, quasars also serve as cosmic markers, allowing scientists to probe the fabric of the universe. Their light can be used to study the intergalactic medium and the expansion of the universe. Each quasar carries a unique story from its time of emission, giving us insights into the conditions that existed billions of years ago. As researchers continue to observe and study these remarkable objects, they unlock the secrets of black holes and the early universe, deepening our understanding of the cosmic landscape. To understand the relationship between black holes and quasars, we first need to look at what each of these phenomena represents. A black hole is a region in space where gravity is so strong that nothing, not even light, can escape its grasp. These cosmic giants form when massive stars exhaust their nuclear fuel and collapse under their own gravity. Quasars, on the other hand, are some of the brightest and most energetic objects in the universe. They are essentially supermassive black holes at the centers of distant galaxies, actively consuming vast amounts of gas and dust. As matter spirals into a supermassive black hole, it forms an accretion disk, a swirling mass of gas that heats up and emits tremendous amounts of energy, often outshining entire galaxies. This is what we observe as a quasar. Despite being located billions of light years away, their light travels vast distances to reach us, allowing us to glimpse the universe as it was in its early stages. The intense luminosity of quasars makes them essential markers for studying the formation and evolution of galaxies through cosmic time. Now, let's delve into the concept of cosmic terror. This idea stems from the immense scale and power of these astronomical bodies. The realization that supermassive black holes exist at the centers of many galaxies, including our Milky Way, can evoke a sense of vulnerability in us. It's a reminder of how small we are in the grand tapestry of the universe, and how cosmic forces operate on a scale far beyond our comprehension. The energy emitted from a quasar can be so immense that it influences star formation in its host galaxy, acting almost as a cosmic bulldozer, shaping the very structure of the universe. In this light, black holes and quasars illustrate not only the vastness and complexity of the cosmos, but also the delicate balance between creation and destruction. As we reflect on these enigmatic entities, we're invited to ponder our place in the universe and the fundamental forces that govern it. The relationship between black holes and quasars offers a fascinating glimpse into the profound nature of cosmic reality, merging scientific wonder with existential contemplation. Quasars, short for quasi-stellar objects, are among the most powerful and distant sources of energy in the universe. They are formed from supermassive black holes actively pulling in gas and dust, which heats up and emits incredible amounts of light and radiation as it spirals inward. Because of their intense brightness, some quasars can outshine entire galaxies, making them visible even from billions of light years away. This extraordinary power leads to the intriguing question of whether they can emit signals that we here on Earth can detect. Indeed, quasars do emit electromagnetic signals across a wide range of wavelengths, including visible light, ultraviolet, X-rays, and radio waves. These signals can travel vast distances through space to reach our telescopes. Scientists have already detected such radiation, allowing us to study quasars and gain insights into the early universe, galaxy formation, and black hole activity. The signals from these distant entities provide a cosmic view of conditions existing billions of years ago, making quasars a sort of time capsule for researchers. Detecting signals from quasars does more than just expand our understanding of the universe. It also raises fascinating possibilities about communication across cosmic distances. If powerful enough, quasars could potentially emit signals that might be interpreted as intentional, much like how astronomers search for signals from advanced civilizations elsewhere in the universe. However, it is important to clarify that the radiation we detect from quasars is a natural phenomenon and not a message from an intelligent source. Quasars not only shine brightly across the cosmos, but also serve as essential tools for unraveling the mysteries of the universe. Their emissions enrich our understanding of cosmic evolution and the mechanics of black holes, while simultaneously sparking our imaginations about the potential for communication in the vastness of space. As we continue to explore these enigmatic objects, we approach the thrilling frontier where astronomy meets the possibility of life beyond Earth. Quasars, short for quasi-stellar objects, are among the most powerful energy sources in the universe. They are found at the centers of distant galaxies and are powered by supermassive black holes that are rapidly consuming gas and dust. As material spirals into these black holes, it heats up and emits staggering amounts of energy in the form of light, radio waves, and X-rays. This immense energy output raises significant concerns for researchers, as it can provide crucial insights into cosmic processes and the evolution of galaxies over time. One primary reason researchers are concerned about quasars relates to their impact on their surroundings. The intense radiation emitted by quasars can influence star formation in the host galaxy. When quasars shine so brightly, their energy can heat the surrounding gas and push it away, preventing new stars from forming. This phenomenon complicates our understanding of galaxy development, as the balance between energy output and star formation is pivotal in determining a galaxy's history and future. Additionally, studying the energy output of quasars can help researchers understand fundamental cosmological questions. For example, they act as beacons, illuminating the fog of gas and dust that permeates the universe. By observing quasars at various distances from Earth, scientists can peer back in time, gathering vital information about the early universe. The energy levels of these quasars provide clues about the conditions that prevailed when they were formed, helping to piece together a more comprehensive history of cosmic evolution. Finally, researchers are also mindful of the relationship between quasars and dark matter. The energy emitted from these extraordinary objects may shed light on the behavior of dark matter at vast scales. By examining the correlation between quasars and their environments, scientists can gain valuable insights into the unseen forces shaping the universe. The study of quasars thus extends beyond mere curiosity. It touches on the fundamental questions of existence, space, and time that intrigue us all. Quasars, or quasi-stellar objects, are among the most captivating celestial phenomena we can observe. They are essentially the bright hearts of distant galaxies, powered by supermassive black holes at their centers. As matter spirals into these black holes, it heats up to extraordinary temperatures, releasing immense amounts of energy that can far outshine entire galaxies. However, the fascinating aspect of quasars lies in their varying characteristics, which can shift depending on how we observe them. When astronomers study quasars, they often look at different wavelengths of light, such as radio, infrared, optical, ultraviolet, and X-rays. Each wavelength reveals different features of the quasar. For instance, in radio observations, certain quasars can appear as giant jets of material extending millions of light-years into space. These jets are sometimes influenced by the magnetic fields around the black hole. In contrast, optical and ultraviolet observations tend to highlight the immense brightness resulting from the energy produced as the surrounding material accelerates towards the black hole. Moreover, the distance of a quasar from Earth plays a critical role in how we perceive its characteristics. Quasars that are nearer to us can appear more stable and consistent in light output, whereas those that are farther away might exhibit variations in brightness due to our current technology limitations and shifts in their immense distances. Intriguingly, the redshift of the light we observe can indicate how fast the universe is expanding, and consequently the age of the quasar, as light from these objects has taken billions of years to reach us. So the next time we gaze at a quasar, we recognize that what we see is just one slice of a much more complex and dynamic cosmic picture. These luminous beacons provide us not only with insights into their own immense energy output, but also with glimpses into the early universe, helping to unravel the mysteries of cosmic evolution and the nature of gravity in extreme conditions. Each observation unfolds a layer, revealing the stunning diversity and characteristics of these astronomical wonders. Quasars, or quasi-stellar objects, are some of the most luminous and powerful entities in the universe. They are thought to be powered by supermassive black holes at the centers of distant galaxies. As matter spirals into these black holes, it heats up to incredible temperatures, producing immense amounts of energy that can be seen across vast cosmic distances. This energy output is so intense that a single quasar can outshine its entire host galaxy, making it an incredible beacon of light in the depths of space. The presence of quasars offers valuable insights into the early universe. They typically became prominent around 10 billion years ago, during a period of rapid galaxy formation and evolution. By studying quasars, astronomers can gather information about the conditions of the universe during that time, including the gas and dust that were available for star formation. This helps us understand how galaxies grew and evolved, alongside the quasars that fueled their growth. Moreover, quasars influence their surroundings in significant ways. Their intense radiation can heat and expel gas from their host galaxies, regulating star formation. This feedback mechanism is crucial in shaping the structure and evolution of galaxies. When a quasar releases energy, it can prevent surrounding gas from cooling and collapsing into new stars, effectively determining the rate at which new stars can be born and the overall evolution of the galaxy. In a broader sense, quasars also contribute to our understanding of the universe's expansion. The light from these distant objects takes billions of years to reach us, allowing astronomers to study how the universe has changed over time. By measuring the properties of quasars, scientists can gather data on the expansion rate of the universe and test theories about its ultimate fate. Quasars serve as cosmic lighthouses, illuminating not only their own galaxies, but also providing critical clues about the universe's history and evolution. Quasars, the incredibly bright centers of distant galaxies powered by supermassive black holes, can provide valuable insights into the nature of dark matter. One of the intriguing theories suggests that by studying the light from quasars as it passes through the universe, we can gather information about dark matter's distribution and effects. Because quasars are so far away, their light travels across vast distances and is influenced by the gravitational fields of any matter it encounters along the way, including dark matter. When a quasar's light is bent due to the gravity of intervening objects, a phenomenon known as gravitational lensing occurs. This lensing effect allows astronomers to map the dark matter around galaxies, which does not emit light and can't be seen directly. By analyzing the patterns of light around a quasar, scientists can deduce the presence and distribution of dark matter in the universe, leading to more precise models of how these unseen materials shape galaxies. Furthermore, quasars can be used as cosmic probes that reveal how dark matter interacts with visible matter. In regions where dark matter is thought to be concentrated, the light from quasars can be distorted in recognizable ways. This enables researchers to infer the gravitational influence of dark matter and how it influences galaxy formation and structure on a cosmic scale. So, as we look deeper into the universe through the eyes of quasars, we touch on the mysteries of dark matter. By harnessing their brilliance and unique positions, astronomers are piecing together a clearer picture of this elusive component of our universe, moving us closer to understanding not just what dark matter is, but how it fits into the grand tapestry of cosmic evolution. Quasars, those incredibly bright and distant objects powered by supermassive black holes at the centers of galaxies, have fascinated astronomers since their discovery. One of the most intriguing aspects of quasars is their variability. They can change in brightness over time. This variation can occur over various timescales, from days to years, revealing much about the dynamics of these celestial entities. Researchers have found that the brightness of a quasar can fluctuate significantly due to various factors, including the accretion of material onto the supermassive black hole. As gas and dust spiral into the black hole, intense energy is released, causing sudden spikes in brightness. These changes can help astronomers understand the environment surrounding the black hole, providing insights into the dynamics of material falling in and the influence of magnetic fields. Long-term studies have shown that quasars can also exhibit systematic changes in brightness over years or even decades. Some appear to dim gradually, possibly due to changes in the disk of material around the black hole or due to interactions with surrounding gas clouds. These long-term trends assist scientists in piecing together the evolutionary history of the quasar and the galaxy it resides in, enhancing our understanding of the universe's structure. The variability of quasars is not only a testament to their energetic nature, but also a key tool for astronomers. By studying these fluctuations, researchers can refine their models of black holes and the mechanisms that govern their growth. Each flicker of light from these distant beacons deepens our understanding of the cosmos and our place within it, offering a glimpse into the intricate dance between light, matter, and gravity on a grand scale. Cosmic rays are highly energetic particles that travel through space at nearly the speed of light. They originate from various sources, including the Sun and distant supernovae, blasting through the universe and occasionally making their way to Earth. When we think of cosmic rays, we often picture tiny particles, like protons and atomic nuclei, racing through the cosmos. In fact, a small number of these particles are also heavy nuclei created in extreme environments, such as exploding stars. These cosmic rays can impact Earth with considerable intensity, especially during solar flares or periods of increased solar activity. Although our planet is protected by a magnetic field and a thick atmosphere, these barriers are not impenetrable. Some cosmic rays manage to penetrate the atmosphere, leading to interactions that can potentially pose a risk to living organisms. When cosmic rays collide with atmospheric atoms, they produce showers of secondary particles, spreading their energy over a wide area. One of the significant concerns associated with cosmic rays is their potential for causing cellular damage. These high-energy particles can break down molecular structures and even alter DNA. For multicellular organisms, including humans, this can lead to harmful mutations, which may increase the risk of cancers and other health issues. In space, away from Earth's protective layers, astronauts are especially vulnerable to these cosmic rays, raising critical questions about the safety of long-duration space missions. Despite these threats, cosmic rays have also sparked a sense of intrigue within the scientific community. Researchers study them extensively to understand their origins and the processes that govern their behavior. They also shed light on the nature of the universe itself, helping us to unlock secrets about stellar explosions and the fabric of spacetime. In contemplating the significance of cosmic rays, we are reminded of the delicate balance that sustains life on Earth amidst the relentless forces of the cosmos. Cosmic rays are among the universe's most intriguing phenomena. They are essentially high-energy particles that travel through space, and their origin can be traced back to some of the most violent events in the cosmos. Most cosmic rays are thought to come from supernova explosions. These are the spectacular end-of-life events of massive stars. During a supernova, immense energy is released, accelerating particles to nearly the speed of light. This process creates a rich source of cosmic rays, which then embark on a journey through the universe. Once these particles are released, they soar through the vastness of space, bombarding the universe from all directions. Their journey is not straightforward. Cosmic rays interact with the magnetic fields of stars and galaxies, which can change their paths and cause them to scatter in unpredictable ways. The result is a cosmic dance where these particles traverse vast distances, often taking thousands or even millions of years to reach their destination. Interestingly, cosmic rays can originate from other sources as well. High-energy particles can also be propelled from active galactic nuclei, which are regions surrounding supermassive black holes. In such locations, matter falls into the black hole, generating immense energy that can accelerate particles to create cosmic rays. Additionally, our own sun contributes to this cosmic mix, particularly during solar flares and coronal mass ejections, which send charged particles hurtling into space. As cosmic rays reach Earth, they interact with the atmosphere, producing showers of secondary particles which can be detected. The study of cosmic rays not only helps us understand high-energy processes occurring in the universe, but also provides insights into fundamental physics, helping researchers peel back the layers of the universe's most puzzling mysteries. Each cosmic ray is a tiny messenger, carrying information about the cosmos from its distant origins, a testament to the dramatic life cycles that play out in the universe. Cosmic rays are high-energy particles originating from outer space, and they interact with the Earth's atmosphere and surface. When these particles collide with atoms in our atmosphere, they can produce secondary particles, which can then reach the surface. For biological organisms, including humans, the effects of cosmic rays can be both direct and indirect, affecting our health and even potentially influencing the evolution of life itself. One of the most significant effects of cosmic rays is exposure to radiation. When these high-energy particles pass through living tissue, they can cause ionization, essentially knocking electrons off atoms. This process can lead to damage in DNA, potentially causing mutations. In high doses, exposure to cosmic rays can increase the risk of cancer and other illnesses. Astronauts, for example, are at a higher risk due to their exposure to cosmic rays while in space, where the Earth's protective atmosphere is weaker. Interestingly, not all effects of cosmic rays are harmful. Some studies suggest that low levels of cosmic radiation might play a role in stimulating biological processes. For instance, These rays can influence the rates of mutation and adaptation in certain organisms. In this way, cosmic rays might contribute to the broader tapestry of evolution by occasionally providing the necessary genetic diversity that allows species to adapt to changing environments. Furthermore, research is ongoing into the long-term effects of cosmic rays on human health, particularly as space exploration becomes more prevalent. As we venture further into space, understanding how cosmic rays impact biological systems will be crucial. Scientists are working on shielding technologies and protective measures to mitigate these effects, ensuring that future astronauts can explore the cosmos with lower risks to their health. Ultimately, cosmic rays remind us of our connection to the universe and the complex interactions between the cosmos and life on Earth. Cosmic rays, high-energy particles originating from outer space, interact with Earth's atmosphere and can occasionally reach the surface. These particles primarily consist of protons and atomic nuclei, traveling at nearly the speed of light. Their journeys through the universe can span millions of years, but when these cosmic particles collide with atmospheric molecules, they can produce cascades of secondary particles and even radiation. This phenomenon has implications for technology and communication, particularly in our increasingly digital world. One significant effect of cosmic rays is their potential to disrupt electronic systems. For instance, in satellites orbiting the Earth, these energetic particles can interfere with onboard electronics, potentially leading to data corruption or even complete system failures. This can have serious consequences for communication satellites, affecting everything from telephone calls to internet connectivity. Engineers must design satellite systems with shielding and redundancy to mitigate such vulnerabilities against these cosmic forces. In addition to satellites, cosmic rays can also impact ground-based technology. High-energy particles can generate single-event upsets, brief glitches in computer memory systems. These moments can cause data errors in servers, leading to erroneous information being processed or stored. As more of our vital services and infrastructure, like power grids and communication networks, rely on digital technology, understanding and managing the risks posed by cosmic rays becomes crucial. Given the modern reliance on technology, the influence of cosmic rays reminds us of the interconnectedness of our existence with the larger universe. The challenge for scientists and engineers is to enhance the resilience of our technology against these cosmic phenomena while continuing to push the boundaries of exploration and understanding in both science and technology. Cosmic rays are high-energy particles originating from outside our solar system, traveling through space and occasionally colliding with Earth's atmosphere. When they strike, they can create secondary particles and showers of energy that have been shown to have intriguing effects on the Earth's atmosphere. One of the more surprising connections is their potential role in cloud formation. As cosmic rays interact with the atmosphere, they can ionize particles, leading to the creation of cloud condensation nuclei, which are essential for cloud formation. Researchers have proposed that fluctuations in the intensity of cosmic rays could influence the amount of cloud cover. More cosmic rays might correlate with increased cloud formation, potentially leading to cooler surface temperatures, while fewer cosmic rays could mean less cloud cover and a warmer planet. This relationship has sparked ongoing debate in the scientific community about the extent to which cosmic rays might impact the climate, especially considering that human-induced factors like greenhouse gas emissions are the primary drivers of current climate change. Studies have attempted to quantify this cosmic ray influence, particularly during periods of low solar activity when the Earth experiences a higher influx of cosmic rays. Some scientists believe this could offer insights into past climate patterns, helping to understand naturally occurring climate variations over geological timescales. However, it's essential to recognize that while these effects are fascinating, they are only part of a larger puzzle regarding climate dynamics. As the research progresses, and while cosmic rays may offer some clues to understanding climate change, it's vital to remember the dominant role of human activities in the ongoing changes we observe today. This complexity underlines the importance of a multifaceted approach to climate science, integrating insights from various fields to piece together the intricate interplay between cosmic phenomena and our planet's climate. Scientists study cosmic rays using a variety of techniques that allow them to gather data about these high-energy particles that constantly bombard Earth from outer space. One of the primary methods involves the use of ground-based observatories. These facilities are equipped with large arrays of detectors that can capture the secondary particles generated when cosmic rays collide with the atmosphere. By analyzing the patterns and energies of these secondary particles, researchers can infer the properties of the original cosmic rays. Another exciting approach is the deployment of satellites in orbit. These satellites can directly measure cosmic rays in space, free from the distortions of the atmosphere. Advanced instruments aboard these spacecraft capture incoming particles, providing valuable information about their energy, composition, and origin. Additionally, balloon experiments are conducted to lift detectors high into the atmosphere, allowing scientists to observe cosmic rays in a less obstructed environment, albeit for limited periods and at great altitudes. Despite these progressive methods, scientists face significant challenges when studying cosmic rays. For instance, cosmic rays come in a variety of energies, but the most energetic ones are extremely rare, making it difficult to collect enough data to draw comprehensive conclusions. Waiting for these rare particles to collide with Earth can be like watching for a specific star to appear in a vast night sky. Moreover, cosmic rays can interact with the Earth's magnetic field, which deflects some particles and complicates where and how they can be measured. Environmental factors also pose challenges. Cosmic rays can be influenced by solar activity, meaning that their flux can vary significantly based on solar cycles. This can introduce variability in the data that scientists must account for. Additionally, protecting detectors from background radiation and ensuring the accuracy of instruments adds further layers of complexity. Despite these hurdles, the ongoing study of cosmic rays not only helps us understand the fundamental processes of the universe, but also provides insights into high-energy astrophysical phenomena and particle physics at cosmic scales. Cosmic rays, high-energy particles that come from outer space, have been a subject of intrigue and concern for scientists since their discovery in the early 20th century. One of the notable historical incidents occurred during the early days of nuclear testing in the 1940s and 1950s. With the advent of atomic bomb detonations, particularly in the atmosphere, scientists raised alarms about the potential increase in cosmic ray intensity caused by nuclear explosions. This concern stemmed from the understanding that such blasts could impact the Earth's atmosphere and possibly lead to a cascade of secondary particles, which would include cosmic rays. Another significant event happened in May of 1986, when a solar particle event coincided with a shuttle launch. As the Space Shuttle Challenger was preparing for its flight, scientists detected an abnormal surge in cosmic ray activity from the Sun. Though operators made adjustments, the increased exposure to cosmic rays led to concerns about the safety of astronauts during such solar events. This highlighted the importance of monitoring cosmic rays, emphasizing how space weather can impact human activity in space. In the early 21st century, researchers also observed a spike in cosmic ray activity linked to a major solar storm in 2003. This solar storm unleashed a torrent of charged particles directed toward the Earth, which raised alarms due to the potential effects on satellites, communications, and even power grids on the ground. As cosmic rays penetrated the atmosphere more forcefully during such events, scientists were reminded of the fragility of technological infrastructure against the piercing backdrop of cosmic phenomena. Lastly, there have been concerns about the long-term effects of cosmic rays on astronauts on deep space missions. Studies show that prolonged exposure to these high-energy particles can lead to increased risks of cancer and other health issues. This ongoing research underscores a vital challenge for future space exploration, reminding us that while the cosmos holds incredible wonders, it also poses significant risks that humanity must understand and mitigate as we venture further into space. Cosmic rays are high-energy particles originating from outer space that constantly bombard the Earth. While these cosmic rays are an integral part of our universe, they also present potential dangers, particularly when it comes to human health and technology. One of the most pressing concerns involves their impact on air travel. At cruising altitudes, commercial aircraft are exposed to higher levels of cosmic radiation than those on the ground. This increased exposure raises the risk of radiation-related health concerns for frequent flyers and aircrew, who may accumulate more radiation over time. astronauts face an even greater threat when they venture into space. In the absence of Earth's protective atmosphere and magnetic field, they are directly exposed to cosmic rays, which can harm their health. Research indicates that extended exposure to these particles may increase the risk of cancer and other health issues, including damage to the nervous system. As space exploration becomes more routine, understanding and mitigating these risks becomes vital for ensuring the safety of astronauts on long-duration missions. Beyond human health, cosmic rays can also interfere with technology. They can disrupt the functioning of satellites, affecting communication systems, GPS, and even weather forecasting. Moreover, as cosmic rays interact with the Earth's atmosphere, they generate secondary particles that can cause additional complications, from random electronic errors in spacecraft systems to creating glitches in data integrity aboard satellites. While cosmic rays are a natural part of our environment, their potential dangers remind us of the delicate balance humans must maintain as we explore and utilize space. Continued research into the effects of cosmic rays will help us develop better protections for the health of both people and technology as we journey into the cosmos. Cosmic rays are high-energy particles that travel through space at nearly the speed of light. They originate from various sources, with some of the most significant being supernovae. When a massive star explodes at the end of its life, it creates shock waves that can accelerate particles to extraordinary speeds. These high-energy particles then escape into the cosmos, contributing to the cosmic ray phenomenon we observe on Earth. Supernovae are fascinating because they not only produce cosmic rays, but also play a crucial role in the distribution of elements throughout the universe. When these stars explode, they scatter heavy elements like iron and carbon into the surrounding space. This material then becomes part of interstellar dust and gas clouds, which may later form new stars and planets. So, in a way, cosmic rays are like messengers sent out from these violent cosmic events, providing us with clues about the life cycles of stars. Interestingly, the connection between cosmic rays and supernovae does not end there. Researchers have found evidence that cosmic rays can help identify the locations of supernova remnants, the leftover material from the explosion. These remnants are often hotspots for cosmic ray production, making them ideal places for scientists to explore further. By studying these regions, we deepen our understanding of both cosmic rays and supernovae, revealing the complex processes that govern the evolution of the universe. Cosmic rays serve as a bridge linking different cosmic phenomena. They emerge from incredibly energetic events like supernovae and provide insights into the dynamics of our universe, the formation of elements, and the evolution of galaxies. This relationship showcases the interconnectedness of cosmic events, reminding us of how even the tiniest particles can have grand implications for our understanding of space. The cosmos brims with wonders, many of which can seem almost surreal. Among the most bizarre interstellar phenomena is the enigmatic object known as a magnetar. A magnetar is a type of neutron star, but it is not just dense and compact. It also possesses an incredibly strong magnetic field, about 1,000 trillion times stronger than that of Earth. This powerful magnetic field generates intense bursts of radiation, often emitting X-rays and gamma rays. The magnetic forces are so potent that if a magnetar were to come close enough to Earth, it could disrupt electronic devices and even alter molecular structures. Another fascinating phenomenon is dark matter. Although it does not emit or absorb light, dark matter makes up about 25% of the universe's mass-energy content. While we cannot observe dark matter directly, its existence is inferred from the gravitational effects it has on visible matter. Galaxies rotate in ways that suggest they have more mass than what we see. This unseen mass is thought to hold galaxies together and influences the formation of cosmic structures. Dark matter challenges our understanding of physics, as it remains one of the greatest mysteries within cosmology. Then there are the astonishing cosmic voids, which are vast expanses of space with very few or even no galaxies. These greatly underpopulated areas can span hundreds of millions of light years. Scientists think these voids formed over billions of years as matter gathered into galaxies and clusters, leaving behind these giant emptinesses. Their existence hints at the universe's large-scale structure, and raises intriguing questions about the seeds of galaxies and the overall evolution of the cosmos. Lastly, let's not overlook the phenomenon of rogue planets. Unlike most planets which orbit stars, rogue planets drift through the galaxy unbound to any star. They can number in the billions and may form through various processes, including the gravitational disruptions during the formation of star systems. Rogue planets could harbor conditions suitable for life, or they might collide with other celestial bodies, causing spectacular cosmic events. Their solitary journey through the dark expanse of space adds one more layer of mystery to our understanding of the universe. Each of these phenomena reminds us that we are just beginning to grasp the complexities of the universe. Observations of unusual star formations offer exciting insights that can challenge established models of astrophysics. Traditionally, astrophysicists relied on theories developed through decades of research, which include the processes of star formation in gas and dust clouds in galaxies. These theories typically follow a predictable cycle. Dense regions within molecular clouds collapse under their own gravity to form stars. However, when scientists observe star formations that don't align with these expected patterns, they are often left with more questions than answers. For instance, astronomers have identified star clusters that appear to be older than their surroundings, or formed in regions where space isn't thought to be conducive to star birth. These anomalies suggest that our understanding of how and where stars form may be incomplete. Questions arise regarding the environmental factors that could lead to such variations. Could there be additional processes at play? Maybe interactions with other galaxies or the influence of dark matter are involved, influencing the dynamics within these regions in ways we have yet to comprehend. Moreover, unusual formations can sometimes indicate the effects of extreme conditions. In some galaxies, the rapid rates of star formation appear to contradict the slow diffusion processes typically described in astrophysics. This idea leads researchers to reconsider how effective turbulence, magnetic fields, or even cosmic rays might be in regulating star formation. With each new observation, our current models are challenged to adapt and incorporate these striking variations. Ultimately, studying these unique star formations enriches our understanding of the cosmos. Each new discovery not only unveils the complexities of our universe, but also drives the collaborative efforts of scientists to refine existing theories. By embracing these anomalies, we expand the boundaries of our knowledge and inch closer to a more comprehensive view of how stars and galaxies evolve. As new technology allows us to peer deeper into space, we can anticipate even more surprises that continue to refine our understanding of the universe around us. Star eaters is a term that refers to a group of incredibly massive stars, specifically those known as black holes. These stellar giants have grown so large and dense that they begin to consume nearby stars, gas, and even dust, leading to their unsettling reputation. The process starts when these supermassive stars reach the end of their life cycle and undergo gravitational collapse, creating an area in space where the gravitational pull is so strong that not even light can escape. What makes these star eaters particularly intriguing is the way they interact with their surroundings. As they feed on nearby material, they often create brilliant displays of energy in the form of X-rays and gamma rays. These emissions are so powerful that they can outshine entire galaxies temporarily. When a star gets too close to a black hole, it can be torn apart in a spectacular event known as Spaghettification, where the extreme gravitational forces stretch the star into long, thin shapes, reminiscent of spaghetti. The unsettling nature of these objects lies in their hidden presence. Black holes cannot be seen directly, as they emit no light. Instead, their existence is inferred from their effects on nearby stars and gas. Observing the movement of these stars can reveal the presence of a black hole lurking close by, allowing scientists to study these mysterious entities. Their uncanny ability to consume anything that ventures too close creates an eerie sense of danger, a reminder of the sometimes violent nature of the cosmos. Furthermore, the concept of a black hole challenging our understanding of space and time also adds to their unsettling nature. They push the limits of our current scientific knowledge, leading to philosophical questions about existence, the nature of reality, and what lies beyond the event horizon, the point of no return. The phenomenon of star eaters encapsulates the awe and mystery of the universe while prompting us to ponder our place within it. As we gaze into the vastness of space, we encounter interstellar phenomena that challenge our understanding and spark our curiosity. These cosmic oddities, such as neutron stars, black holes, and gamma-ray bursts, provide critical insights into the universe's origins. Each of these phenomena stands as a testament to the extreme processes that dramatically shape the cosmos, revealing the complex interplay of forces that existed in the moments immediately following the Big Bang. For instance, neutron stars, remnants of massive stars that have undergone supernova explosions, are incredibly dense. The study of these celestial bodies allows scientists to probe conditions of matter under extraordinary pressures, which can shed light on the forces and particles that were prevalent in the early universe. When a star collapses to create a neutron star, it dramatically compresses its core, resulting in an environment that mirrors the conditions of the universe when it was just a fraction of a second old. Similarly, black holes, particularly supermassive black holes found at the centers of galaxies, may hold clues about the universe's evolution. These elusive giants influence the formation and behavior of galaxies over billions of years. By observing the interaction between galaxies and their central black holes, researchers can infer the growth patterns of these cosmic structures, thereby piecing together the timeline of the universe's expansion and evolution. Gamma-ray bursts, among the most energetic events in the universe, can occur when massive stars collapse or when neutron stars collide. The study of these bursts not only enhances our comprehension of explosive cosmic events, but also provides critical data about the distribution of elements produced during such cataclysms. As these elements spread across the universe, they contribute to the formation of new stars and planets, ultimately weaving the fabric of the cosmos we observe today. Thus, the seemingly bizarre interstellar phenomena do not merely occupy the fringes of our understanding, but are pivotal in unlocking the mysteries of the universe's origins. Supernovae are extraordinary cosmic events that unfold when a star exhausts its nuclear fuel and undergoes a catastrophic explosion. This powerful explosion releases an immense amount of energy, propelling heavy elements like iron and nickel into the surrounding space at incredible speeds. These materials are essential for the creation of new stars, planets, and the very building blocks of life, making supernova an integral part of the cosmic recycling process. However, the aftermath of a supernova is not just about creation. It can also lead to the formation of interstellar anomalies. These anomalies often take the form of shock waves and high-energy particles that flood the surrounding area. As the remnants of the supernova expand, they can accumulate cosmic rays, high-energy particles that travel through space at nearly the speed of light. These cosmic rays can interact with interstellar gas and dust, leading to intriguing phenomena, including the formation of complex structures in the interstellar medium. What makes this process alarming is its potential impact on our understanding of the cosmos and the safety of space exploration. The energy released by supernovae can influence the entire ecosystem of nearby stars and planets, possibly triggering the formation of new stars or even disrupting existing solar systems. Additionally, cosmic rays generated by supernova events can pose a radiation hazard to astronauts venturing beyond Earth's protective atmosphere, highlighting the need for careful consideration of these powerful cosmic phenomena. Thus, while supernovae are vital for fostering the cosmic landscape, their dynamic nature and the interstellar anomalies they generate present both opportunities for discovery and challenges for future exploration. By studying these events, we gain insights into the life cycles of stars and the grand tapestry of the universe, reminding us just how interconnected all aspects of the cosmos truly are. Scientists employ a range of sophisticated techniques to investigate and interpret unusual signals from deep space. The first step in this process often involves the use of radio telescopes, which are massive devices that collect and amplify radio waves from space. These telescopes can be found in remote areas, far away from the noise of human activity, allowing them to pick up even the faintest signals. Once a possible signal is detected, researchers meticulously record its frequency, duration, and any patterns it might exhibit. To discern whether a signal comes from a natural source or a more exotic phenomenon, scientists compare it with known astronomical phenomena. They analyze the signal's characteristics, such as whether it appears to be a continuous wave or a series of pulses. Signals that exhibit regular patterns might suggest artificial origins, prompting further investigation. Additionally, scientists often collaborate with other observatories globally, sharing their findings and cross-referencing data to bolster their understanding. Interpretation involves delving deep into the context of the signal. This can include scrutinizing the surrounding cosmic environment and searching historical data for similar occurrences. When peculiar signals are discovered, they are often subjected to intense scrutiny to rule out interference from Earth-based sources, such as satellites or terrestrial signals that might contaminate the data. Ultimately, if a signal persists and withstands the rigorous investigative process, it might lead to groundbreaking discoveries. These could deepen our understanding of the universe or even suggest the presence of extraterrestrial life. Each unusual signal serves as a reminder of the vastness of the cosmos and our endless thirst for knowledge about what lies beyond our planet. As we gaze into the cosmos, scientists frequently encounter mysterious signals that leave us both intrigued and puzzled. One of the most famous examples is the repeating fast radio bursts, or FRBs. Discovered in 2007, these high-energy astrophysical phenomena can last mere milliseconds, yet release as much energy in that short time as the Sun emits in an entire year. Some of these bursts come from distant galaxies, and while we've pinpointed their general locations, their origins remain largely unknown, prompting a range of theories from neutron stars to possible extraterrestrial technologies. Another perplexing signal is the WOW signal, detected in 1977 by astronomer Jerry R. Ehman. This strong and unusual radio signal lasted for 72 seconds and was so intriguing that Ehman scribbled "WOW" in the margins of the data printout. Despite numerous attempts to track it down or identify its source, the signal has never been detected again. Some speculate it may have originated from a comet or natural astrophysical phenomena, while others hold on to the hope that it could have been a message from another civilization. More recently, researchers have been tracking what are known as potential techno-signatures. These are signals or patterns that could indicate technological activity, hinting at possible advanced civilizations out there. One study in 2021 reported a particularly puzzling signal, a peculiar pattern from a distant star system that drew heightened interest. Though further observations have not conclusively explained it, the potential for discovering an artificial origin keeps scientists on alert, refreshing our imaginations about life beyond Earth. Finally, there's the current investigation into signals coming from an area of the Milky Way called the Galactic Center. Specifically, a mysterious 521 Hz signal has been recently detected, which scientists are still trying to decipher. It may relate to the interactions of matter with our galaxy's supermassive black hole or some unknown cosmic event. Each of these signals, unexplained and enigmatic, stirs the scientific community's curiosity, ensuring that the quest to understand our universe, and perhaps the existence of other life, continues to be a thrilling endeavor. Gravitational waves are one of the most fascinating discoveries in modern astrophysics, seamlessly weaving into the complex tapestry of interstellar phenomena. These ripples in spacetime, created by the acceleration of massive objects, like merging black holes or neutron stars, offer us a brand new way to observe the universe. Through the detection of these waves, scientists have opened a window into cosmic events that were previously beyond our reach, expanding our understanding of both gravity and the cosmos itself. When two massive objects collide, the disturbance they create sends out gravitational waves that travel across the universe at the speed of light. This phenomenon is akin to tossing a stone into a still pond, where the ripples spread outwards from the point of impact. The first direct observation of gravitational waves occurred in 2015, originating from the collision of two black holes about 1.3 billion light-years away. This breakthrough not only confirmed a prediction made by Albert Einstein in his general theory of relativity, but also marked the dawn of a new era in astronomy. Interstellar phenomena are filled with bizarre and extreme events, and gravitational waves provide insights that help us decode these mysteries. For instance, when we detect waves from an event like a neutron star merger, we gain valuable information about the properties of these stars, such as their mass and density. This allows us to investigate the fundamental nature of matter and the conditions that exist under such extreme gravitational influences. These observations link directly to other exotic phenomena, such as gamma-ray bursts and kilonovae, which are bursts of light resulting from these high-energy cosmic collisions. Gravitational waves not only deepen our understanding of the universe's most enigmatic occurrences, but also highlight the intricate connections between various cosmic events. They shift our perspective from a purely visual understanding of space, based on traditional light observation, to an exciting realm of auditory signals that tell us about the universe's most violent and fascinating processes. This exploration enriches the narrative of interstellar phenomena, inviting us to listen to the symphony of the cosmos and revealing stories written in the fabric of spacetime itself. Interstellar events such as supernovae or the collision of black holes can profoundly challenge our understanding of time and space due to their inherently complex nature and dramatic effects on the fabric of the universe. These events can produce gravitational waves, which ripple through spacetime and alter our perceptions of both time and distance. When massive objects in space interact, they can stretch and compress the space around them, leading to phenomena that challenge our traditional views. Moreover, some of these cosmic happenings occur under conditions where the laws of physics as we understand them may not apply neatly. For instance, near the event horizon of a black hole, time itself appears to behave differently. To an outside observer, time slows down for an object falling into a black hole, while for that object, time continues at its normal pace. Such scenarios raise profound questions about the nature of time itself, leading to debates about whether time is absolute or relative. Another intriguing aspect is related to the vast distances involved in interstellar events. Light from these explosions or collisions can take millions or even billions of years to reach us. This means we are observing events that happened in the distant past, forcing us to reconcile what we understand about the present universe with ancient cosmic history. Each light year we glimpse back in time further complicates the straightforwardness of how we perceive time and causality. Finally, these interstellar occurrences can inspire new theories that push the boundaries of our scientific paradigms. They encourage scientists to refine existing theories, such as Einstein's theory of relativity, or even to look for new unified theories of physics. This continual evolution of thought not only enriches our understanding of the universe, but also reminds us how much we still have to learn, inviting a sense of wonder about the cosmos and our place within it. Time dilation is a fascinating concept rooted in Albert Einstein's theory of relativity. It refers to the difference in the elapsed time as measured by two observers, due to a relative difference in velocity or gravitational field between them. Simply put, time can pass at different rates for people moving at different speeds or experiencing different gravitational forces. For instance, if one twin travels on a space journey at a significant fraction of the speed of light, while the other remains on Earth, the traveling twin will age more slowly compared to their sibling. This is often illustrated through the twin paradox, a thought experiment that captures the imagination. What makes time dilation particularly intriguing and perhaps even frightening is the way it challenges our everyday understanding of time. We tend to perceive time as a constant, an unchanging backdrop to our lives. However, the reality is that time is much more fluid than our senses suggest. When traveling close to the speed of light, time drastically slows down. This can lead to scenarios where astronauts return to a vastly different Earth than the one they left, experiencing what feels like years passing while only a relatively short time has elapsed for them. Moreover, time dilation also occurs in strong gravitational fields. The deeper one goes into a gravitational well, like that of a massive planet or star, the slower time moves compared to someone farther away. This means that if you were to spend time on a massive black hole's event horizon, which is purely theoretical at this point, you could theoretically return to find that significant time has passed for the rest of the universe, but only a brief moment for you. Such implications can evoke feelings of existential dread as they make us realize that our lives are bound to a flow of time that can vary drastically beyond our immediate perception. Time dilation not only reshapes our understanding of time itself, it also raises profound questions about the nature of reality, our existence, and how we relate to the universe. It provokes a sense of wonder and fear alike as we grapple with a universe so different from the straightforward linear experience of time that we take for granted in our daily lives. Time dilation is a fascinating concept rooted in the theory of relativity introduced by Albert Einstein over a century ago. At its core, time dilation suggests that time does not flow uniformly for everyone. Instead, it can stretch or contract depending on the relative speeds of observers or the strength of gravitational fields they experience. This challenges our everyday understanding of time as a steady, unchanging backdrop against which events unfold. In practical terms, imagine two identical clocks. One remains on Earth, while the other travels into space at high speeds. When the traveling clock returns, it will show less elapsed time than the Earth clock. This phenomenon has been confirmed by various experiments, including those involving precise atomic clocks placed on airplanes. The implications are profound, as they imply that time can move differently depending on your circumstances, fundamentally shifting our perception of reality. But why is this significant? Time dilation hints that our connections to the universe are not as straightforward as they might seem. If we think about existence and reality, we realize that if one person experiences time differently than another, their realities could diverge based on their individual experiences and trajectories through space and time. This raises philosophical questions about the nature of existence itself. Are we all experiencing the same reality, or is each moment uniquely lived? Furthermore, in a universe where time can bend and twist, the very fabric of reality becomes a tapestry woven with the threads of different experiences. This understanding fosters a deeper appreciation of the complex nature of the cosmos, a reminder that our human perceptions, shaped by consistent timelines, are just one way to engage with the mysteries of existence. As we continue to explore the universe, the revelations about time and its fluidity invite us to reconsider what we think we know about reality. Time dilation is a fascinating consequence of Einstein's theories of relativity, particularly when it comes to space travel. To put it simply, time dilation occurs because the speed of light is constant, regardless of how fast you're moving. As a result, the faster a spacecraft travels closer to the speed of light, the more pronounced the effect of time dilation becomes. For astronauts embarking on journeys through space at high speeds, their experience of time would differ significantly from those of us remaining on Earth. Imagine, for example, a spacecraft traveling out to a distant star system at a significant fraction of light's speed. For the astronauts aboard, the journey might take just a few years. However, back on Earth, decades or even centuries could pass. This means that, while the astronauts age just a few years, their friends and family on Earth could age decades. Such a scenario raises profound questions about relationships and the passage of time itself, not to mention the complexities of communication with loved ones left behind. This phenomenon can also have implications for missions beyond our current capabilities. As we contemplate sending humans to Mars or beyond, we must factor in how time dilation could affect crew dynamics and mission planning. For far-flung missions, understanding time in the context of relativity could help scientists and mission planners create realistic calendars and schedules to ensure that the crew remains orientated and connected to their homes. In conclusion, the real-world implications of time dilation for space travel stretch beyond mere theoretical musings. They influence how we think about space exploration and challenge our understanding of time as a universal constant. As we continue to venture into the cosmos, these insights will shape not just our journeys, but also the very fabric of human experience in deep space. To grasp the fascinating effects of time dilation caused by black holes, it helps to understand a concept central to Einstein's theory of relativity. Time dilation describes how time moves at different rates depending on the observer's position in a gravitational field. The stronger the gravitational field, the more pronounced the effect. Black holes represent the pinnacle of gravitational forces in our universe, where their gravity is so intense that it governs everything that comes close to them, including the flow of time. As matter approaches a black hole, it experiences immense gravitational pull. This is particularly evident near what we call the event horizon, the boundary beyond which no escape is possible. For an outside observer, a clock that is near the event horizon ticks much more slowly compared to a clock far away from the black hole. This means that while only a short time may appear to pass for an object falling into a black hole, many years or even centuries could elapse for an observer stationed safely far away. This extreme variation intrigues physicists and challenges our understanding of time itself. Moreover, the mass of a black hole itself plays a crucial role in amplifying these effects. The more massive a black hole, the stronger its gravitational pull becomes, and thus the greater the time dilation experienced as one approaches it. A supermassive black hole at the center of a galaxy can create time experiences that seem almost surreal. Near such colossal entities, moments for observers can stretch into what feels like an eternity, making the ordinary flow of time appear infinite. These remarkable properties of black holes not only prompt us to rethink time, but they also serve as cosmic laboratories for testing the theoretical predictions of relativity. As we continue to probe deeper into the mysteries of black holes, scientists hope to unlock the secrets of how time and space interweave in the fabric of our universe, inviting us to imagine the profound implications such discoveries hold for our understanding of existence itself. Time dilation is one of the most fascinating aspects of Einstein's theory of relativity. As astronauts approach speeds close to that of light, an unsettling phenomenon occurs. Time for them begins to move more slowly compared to observers back on Earth. This means that while they might experience only a few years of travel, many more years could pass for those waiting at home. Imagine embarking on a journey through the cosmos, returning to find friends and family have aged decades, while you feel as though only a few short years have passed. This surreal effect can create emotional turmoil. Consider a scenario where a father decides to travel on a spacecraft reaching near light speeds, hoping to discover distant worlds. As he departs, his young children wave goodbye, but depending on the length and speed of his journey, he may return to find them grown adults, living lives full of experiences he missed out on. The disconnect between his expectations and the reality of time's passage can lead to profound feelings of loss and isolation. Moreover, this scenario isn't just a fantastical story. It's grounded in the laws of physics. While the astronauts are experiencing their own reality in their fast-moving spaceship, the rest of the universe continues on, unfazed by their incredible journey. This creates a rich tapestry of existential questions. What does it mean for relationships and human connections when time behaves so differently for different observers? Ultimately, time dilation serves as a constant reminder of the relative nature of our universe. While we may have a shared understanding of time as a linear experience, the truths of relativity force us to confront the complexities of time itself. For astronauts, the challenge lies not just in navigating the vastness of space, but in reconciling the emotional distances that can grow from these relativistic effects. Time dilation is a fascinating consequence of Einstein's theory of relativity, and several experiments have effectively illustrated this intriguing concept. One of the most famous experiments involved atomic clocks placed on high-speed jets. In a classic study conducted in the late 20th century, scientists flew atomic clocks around the world on commercial airliners. Upon their return, the clocks on the planes showed slightly less elapsed time compared to those that remained on the ground, confirming time dilation caused by their high velocity. Another significant experiment took place on the surface of the Earth. It examined the effect of gravity on time, a concept also part of relativity. Clocks were placed at different altitudes, with one clock at the top of a mountain and another at sea level. The clock positioned at the higher elevation ticked slightly faster than the one at sea level. This difference was due to the weaker gravitational field at higher altitudes, demonstrating how gravity can affect the flow of time. Furthermore, observations of particles such as muons have also provided evidence of time dilation. Muons are unstable subatomic particles that are created when cosmic rays collide with the Earth's atmosphere. They travel close to the speed of light and, due to their high velocity, have a longer decay time than those at rest. This increase in their lifespan, as observed by scientists on ground detectors, directly showcases time dilation in action, as the muons experience time at a slower rate than we do. These experiments and observations emphasize the mind-bending nature of time and space. Each demonstration brings us closer to understanding our universe and reaffirms the profound implications of relativity. Time dilation is not just a theoretical concept, but a measurable reality, showcasing the remarkable dance between time, speed, and gravity in our cosmos. The concept of time distortion stirs a deep sense of unease because it challenges our fundamental understanding of reality. In our daily lives, we experience time as a linear progression, moments slipping from past to present and into the future. When we think about time not functioning as we anticipate, it creates a disruption. This uncertainty can evoke feelings of helplessness or fear because it threatens the stability and predictability that we rely on in our lives. One of the most fascinating aspects of time distortion is how it can alter human experiences. For instance, the phenomenon of time slowing down during traumatic events can be unsettling. Many people report feeling as though time has stretched, allowing them to notice every detail of a moment, almost as if their brain is processing information at an accelerated rate. This experience can leave a person disoriented and confused, adding layers of fear to an already alarming situation. Moreover, in the realm of theoretical physics, discussions about time travel or the possibility of time loops challenge our perceptions even further. Questions arise: what if we could revisit past mistakes, or, conversely, if we become trapped in a phase of time we cannot escape? These ideas can lead to existential reflections on the nature of our choices and the impact of time on our existence, intensifying feelings of anxiety. Time distortion invokes fear because it undermines our grasp of reality. It forces us to confront unsettling uncertainties about life and our place within it. Engaging with these concepts can awaken a profound curiosity about the nature of time itself, yet this same allure can evoke a disconcerting sense of vulnerability and existential dread, reminding us of the limited control we have over our own lives. Time dilation, a fascinating concept rooted in the theory of relativity, occurs when an object's speed approaches that of light or when it is in a strong gravitational field. As time slows down for an object moving at high velocities relative to a stationary observer, it raises some intriguing questions, particularly the notion of paradoxes. One well-known example is the twin paradox, where one twin travels in space at near light speed while the other remains on Earth. Upon returning, the traveling twin is younger than the one who stayed home, defying our intuitive understanding of time. This scenario might seem contradictory, but it underscores the relative nature of time. From the perspective of the traveling twin, time proceeds normally. However, from the standpoint of the stationary twin, the clock of the moving twin appears to tick more slowly. The paradox arises because it challenges our conventional view of time as absolute and homogeneous. Instead, time becomes intertwined with speed and gravity, revealing a much more complex universe. These paradoxes highlight the profound implications of time dilation on our understanding of reality. They prompt us to reconsider how we perceive time itself, pushing the boundaries of our concepts and beliefs. The idea that time is not a fixed quantity, but rather a malleable dimension, invites a new layer of exploration in both science and philosophy. The discrepancies brought forth by time dilation serve as a reminder that our intuitive grasp of time can be misleading, urging us to think more deeply about how we experience the universe. In practical terms, understanding these paradoxes is crucial for technologies such as GPS, which must account for the effects of time dilation to provide accurate location information. Without this correction, our navigation systems would drift significantly over time, demonstrating that the principles behind time dilation affect our daily lives as much as they challenge our understanding of the cosmos. By embracing these complexities, we not only expand our scientific knowledge, but also nurture a sense of wonder about the nature of existence itself. Time dilation, a concept rooted in Einstein's theory of relativity, presents fascinating implications for future journeys to distant galaxies. Essentially, time dilation means that time can pass at different rates for observers in different frames of reference. For a spacecraft traveling at speeds close to the speed of light, time for those aboard would slow down relative to those remaining on Earth. This phenomenon becomes especially pertinent when considering long journeys across vast cosmic distances. Imagine embarking on a journey to a galaxy billions of light-years away. If our spacecraft could achieve speeds approaching that of light, the journey could yield surprising results. While decades or even centuries might elapse for those aboard the ship, many more years might pass on Earth. An astronaut who leaves for a distant galaxy and returns might find that generations have gone by at home, while only a few years have taken place inside the spacecraft. This stark contrast in the passage of time opens intriguing possibilities for exploration and understanding. Futuristic travelers could witness events in the universe that have occurred long after they set out, catching glimpses into the distant future of Earth. In a sense, they become time travelers, exploring not just the vast distances of space, but also the dimensions of time itself. However, reaching such incredible speeds remains a daunting challenge with our current technology. The energy requirements alone are monumental, not to mention the engineering hurdles involved in sustaining human life over such extended periods. Despite these challenges, the very concept of time dilation invites us to dream about the potential of cosmic exploration and the mysteries that await us in the great expanse of the universe. The Fermi Paradox is a thought-provoking concept that arises from the contrast between high estimates of the potential for extraterrestrial life in the universe and the apparent lack of evidence for such life. Named after the physicist Enrico Fermi, the paradox poses the question, if the universe is so vast and old, and there are countless stars and planets that could support life, why haven't we found any signs of intelligent life beyond Earth? To understand the paradox, we need to consider the sheer scale of the universe. There are billions of galaxies, each hosting billions of stars, many of which may have planets in their habitable zones where life could exist. Even if intelligent life were relatively rare, the vast number of potential civilizations suggests that we should be seeing indications of their existence, like radio signals or other forms of communication. Yet despite our searching efforts and the technological advancements we have made, we have found no credible evidence of extraterrestrial societies. This absence of contact leads to unsettling implications. One possibility suggests that intelligent life is extremely rare or fleeting. Civilizations might emerge and extinguish themselves before they can communicate across the stars. Another possibility is that advanced life forms may deliberately avoid contact with us, either out of fear, a sense of superiority, or perhaps a set of ethical guidelines that prevent them from interfering with our development. These scenarios evoke a sense of existential unease. If we are indeed alone in a vast and seemingly life-supporting universe, it raises questions about the sustainability of our own civilization and the choices we make. The Fermi Paradox invites us to reflect not only on the nature of life in the cosmos, but also on our own place within it, instilling a deeper appreciation for the rarity and fragility of existence itself. The Fermi Paradox presents a fascinating question in the realm of cosmology. If the universe is so vast and potentially teeming with life, why have we yet to detect any signs of extraterrestrial civilizations? Various theories attempt to address this intriguing conundrum, with some proposing that we are simply not looking in the right way or places. For instance, a popular idea is that advanced civilizations are using communication methods far beyond our current technological capabilities. They might rely on quantum communications or technologies that we have yet to discover, leaving us blissfully unaware of the signals they are sending. Another compelling theory posits that intelligent life is exceedingly rare. While life may exist abundantly in simpler forms, the evolution of intelligent civilizations could be an extraordinarily rare event. This could be due to numerous factors, including catastrophic events that can wipe out species before they can become technologically advanced, or that the necessary conditions for such evolution are so specific that they occur far less often than we assume. This rarity suggests that we might just be one of the very few, or even the only, intelligent life forms in our galaxy, raising profound questions about our own existence. Some theories suggest that advanced civilizations may choose to intentionally hide. Known as the zoo hypothesis, this notion proposes that extraterrestrial beings are observing us, much like zookeepers watching animals in a habitat, but have opted not to make their presence known to ensure we develop without interference. Additionally, a form of this theory implies that advanced civilizations could reach a level of technological sophistication that leads them to abandon space exploration in favor of virtual environments, effectively making interstellar travel and communication obsolete for them. Lastly, there's the Great Filter theory, which proposes that there is a significant barrier to the emergence of advanced civilizations. This filter could exist either in the past, suggesting that most life never evolves intelligence, or it could lie somewhere in the future, indicating that civilizations tend to self-destruct before they reach a level of expansion that allows them to communicate across the stars. The implications of this theory are both sobering and illuminating, as they compel us to reflect on our own technological advancements and the sustainability of human civilization itself in the grand cosmic scheme. Each of these theories contributes to the ongoing conversation about our potential cosmic neighbors, propelling our curiosity about life beyond our planet. The search for extraterrestrial civilizations has captivated scientists and thinkers for decades, driving ambitious efforts to explore the cosmos. Despite our advancements, the absence of evidence suggesting intelligent life beyond Earth stirs a complex mix of curiosity and unease. This scenario raises profound philosophical questions about our existence and the future of humanity within the vast universe. One reason the lack of evidence feels unsettling is the concept known as the Fermi Paradox. Named after the physicist Enrico Fermi, this paradox poses the simple yet striking question: if the universe is so vast and old, brimming with potential for life, where is everyone? The silence from the cosmos can lead to speculation that perhaps advanced civilizations are rare, or worse, that they might not survive long enough to communicate with us. Such thoughts evoke an existential dread, creating a stark reflection on our own fragility. Moreover, the absence of evidence can lead to the unsettling realization that we might be alone in a universe teeming with possibilities. This solitude holds implications for how we view our own species. Are we the most advanced intelligence in our cosmic neighborhood, or could it be that intelligent life, when it emerges, tends to self-destruct before it can reach out to the stars? These questions weigh heavily on scientists who ponder the fate of civilizations, incorporating insights from biology, sociology, and even psychology into this quest for understanding. Ultimately, the search for signs of life beyond our planet is not just about finding others, it's about understanding ourselves. The silence of the universe serves as a stark reminder of our responsibilities as stewards of Earth. As we grapple with our isolation in the cosmos, this quest for extraterrestrial colleagues compels us to consider the choices we make and the legacy we will leave behind, igniting both hope for connection and a somber reflection on our current trajectory as a species. The idea of advanced civilizations existing somewhere in the universe stirs a mix of curiosity and concern. While we often imagine scenarios where contact with advanced beings could benefit humanity, there's a more cautionary perspective. When a civilization is technologically superior, they may view less advanced societies like ours as either a resource to exploit or a potential threat to their existence. One significant concern stems from the potential for resource competition. An advanced civilization might seek the same resources that we depend on, like water or minerals, leading to conflict. In this scenario, humanity could become collateral damage in a much larger cosmic struggle. Moreover, if these civilizations are driven by motives we cannot comprehend, their actions could pose serious risks, threatening our very survival. Another challenge lies in the technological disparity. With access to advanced weaponry or other powerful technologies, contact could turn dangerous quickly. This imbalance may lead to situations where humanity is unable to defend itself against hostile actions. History has shown us that encounters between civilizations at different levels of development can be perilous, where the more advanced entity often imposes its will on the less advanced, sometimes with devastating consequences. Lastly, there's the philosophical and ethical dimension to consider. An advanced civilization might not even recognize us as sentient beings. They could inadvertently interfere with our existence, launching projects that ignore our welfare altogether. The possibility of being rendered an afterthought in the grand narrative of the universe is unsettling, highlighting the thin line between potential discovery and existential risk in our ongoing search for extraterrestrial life. The potential silence of the universe raises profound questions about our understanding of life itself. For decades, scientists have combed through the cosmos, scanning for signs of extraterrestrial intelligence. This search, often encapsulated in the famous phrase, "Are we alone?" hinges on the assumption that if life exists elsewhere, we should eventually detect it. However, as efforts continue without decisive findings, a different narrative unfolds, a universe that may indeed be silent. This silence could suggest that intelligent life is exceedingly rare, perhaps due to unique conditions on Earth that fostered our own existence. The universe is unfathomably vast, containing billions of galaxies, each with countless stars and potential planets. Yet the echoes and signals we seek seem to elude our increasingly sensitive instruments. If intelligent life is scarce, it may hint at tremendous challenges that civilizations face, such as self-destruction or environmental collapse, which could limit the longevity of advanced societies. Alternatively, the quietude of the universe might suggest limits to our own understanding of intelligence and life. The parameters we use to define these concepts are largely shaped by our own experience. If life exists in forms vastly different from what we recognize, those signals may not be recognizable to us, remaining silent by virtue of our narrow perspective. This invites curiosity about what diverse forms life might take across the cosmos and challenges us to expand our definitions. Ultimately, the implications of a silent universe are not signs of defeat, but invitations for deeper exploration. They nudge us toward introspection about our place in the cosmos and the responsibility we hold as intelligent beings. In a universe where we may not find others, we are left to ponder the significance of our existence and the relationships we cultivate with each other and our planet. It cultivates a sense of stewardship, urging us to cherish the biosphere we inhabit and to embrace our quest for knowledge and understanding. The Fermi Paradox presents an intriguing question. If there are so many stars in the universe and countless potentially habitable planets, why haven't we found evidence of extraterrestrial civilizations? This contradiction between high probability and lack of evidence makes scientists scratch their heads. To address this perplexing scenario, one possible explanation is the Great Filter hypothesis. The Great Filter suggests that there are significant barriers or challenges that prevent civilizations from advancing to the point where they can be detected. This filter could exist at various stages of the evolutionary process. It might be that the transition from simple life forms to complex ones is exceptionally rare, or perhaps technological societies tend to self-destruct before they can make contact with others in the cosmos. The mysteries of this filter provoke deep questions about our own existence and future. One compelling notion is that the Great Filter could lie behind us, indicating that our ability to exist and evolve may be an extraordinary achievement. If intelligent life is exceedingly rare in the universe, it suggests that we are among a select few that made it through a series of drastic survival challenges. In this sense, our unique position could be a cause for optimism, implying that life is indeed very special. Conversely, if the filter lies ahead of us, it raises a sobering prospect. It could mean that advanced civilizations inevitably face catastrophic challenges that lead to their extinction. This uncertainty adds a layer of urgency to our understanding of technological development and longevity as a species. Thus, the Fermi Paradox and the Great Filter hypothesis intertwine to create a thought-provoking dialogue about our place in the universe and the fate that awaits us among the stars. The Fermi Paradox presents a thought-provoking conundrum. If the universe is so vast and potentially teeming with life, why have we not encountered any signs of extraterrestrial civilizations? This paradox doesn't only stir curiosity in the realm of science, it also prompts a variety of social implications that can shape our thoughts about humanity's place in the cosmos. One significant implication centers on our understanding of life itself. The paradox encourages discussions on the nature of existence, intelligence, and civilization. It invites us to reflect on our own societal structures, ethics, and even our technological advancements. By examining why other life forms might avoid contact or why they may not exist, we might come to appreciate the fragility of our own civilization, fostering a deeper sense of responsibility for our planet and future. This realization can galvanize efforts towards sustainability and peaceful coexistence on Earth, recognizing that, relatively speaking, we may be just one among many. Furthermore, the prospect of alien life influences our cultural narratives and existential beliefs. From literature to cinema, the theme of extraterrestrial contact often explores profound questions about what it means to be human. These narratives can shape our worldview, inspiring unity among people on Earth or provoking fears of existential threats. In this light, grappling with the Fermi Paradox has the potential to either promote cooperation and collaboration across cultures by emphasizing our shared fate or exacerbate divisions over differing beliefs regarding our significance in the universe. Lastly, the Fermi Paradox leads to introspection about our technological progress and communication efforts with potential intelligent beings. As we set up powerful telescopes and attempt to send signals into space, we must consider who we are as a species and what message we wish to convey. It raises ethical questions about how we portray ourselves to the universe and the decisions we make about exploration. Ultimately, the quest to understand our place in the cosmos changes how we perceive ourselves and each other, igniting a collective journey of discovery that transcends borders and unites us in a shared curiosity about what lies beyond the stars. The Fermi Paradox poses a captivating question: where is everybody? Named after the physicist Enrico Fermi, it highlights the contradiction between the vast number of stars in the universe and the apparent absence of extraterrestrial civilizations. As we continue to explore the cosmos, future discoveries could either clarify this paradox or add layers of confusion, depending on what we find. If we were to discover new exoplanets in the habitable zones of distant stars, it would amplify hopes of finding life beyond Earth. Each new Earth-like planet suggests a greater likelihood that life could have evolved elsewhere. Such discoveries might also lead scientists to re-evaluate the conditions necessary for life, pushing the boundaries of where we search and how we define habitability. Additionally, the detection of biosignatures, which are chemical indicators of life, could signal that we are not alone after all. On the other hand, new findings might also deepen the mystery of the Fermi Paradox. As we learn more about the harsh conditions of space and the challenges associated with the emergence of life, we might realize that life is much rarer than we anticipated. Perhaps we will find that while the ingredients for life are common, the successful evolution of intelligent beings is exceedingly rare. If we find numerous planets with the right conditions but no signs of life, it could make us question why life did not arise there. Ultimately, our journey of discovery in the universe continues to shape our understanding of our place within it. Whether clarifying or complicating the Fermi Paradox, each new finding offers an opportunity to expand our curiosity and reconsider our assumptions. As we look to the stars, the quest for knowledge about life beyond Earth remains one of humanity's greatest adventures, reflecting our desire to connect with the wider cosmos. The ongoing quest to detect extraterrestrial signals embodies our deep-seated desire to connect beyond our own planet. This search is more than just a scientific endeavor. It speaks to a fundamental aspect of human nature, our fear of being alone in the vast universe. As we scan the skies with powerful telescopes and sophisticated technology, we are not simply looking for extraterrestrial life. We are yearning for companionship and validation of our existence in an often incomprehensible cosmos. Every signal we pursue holds the promise of revealing something profound about our place in the universe. The possibility of discovering intelligent beings elsewhere offers hope that humanity is not the isolated product of a solitary blue planet. For many, such a discovery could alleviate existential fears, providing a sense of belonging and shared existence. The thought that we might not be alone brings comfort against the isolating vastness of space, which can feel overwhelming and infinite. Yet the search can also amplify our anxieties. We grapple with questions of what it would mean for humanity if we were to find ourselves alone. Would that signify a failure of our species, or would it encourage us to foster more profound connections among ourselves? As we ponder the implications of extraterrestrial life, we confront our vulnerabilities and the uncertainty of our future on Earth. This duality of hope and fear reveals much about our psyche as we navigate a path forward in a universe that can be both beautiful and intimidating. Ultimately, the pursuit of extraterrestrial signals acts as a mirror reflecting our innermost feelings about existence, connection, and loneliness. In the silence of the cosmos, every echo of a signal, every distant blip, serves as a reminder of our quest for understanding, pushing us to delve deeper not only into space, but also into our own shared human experience. In this ongoing search, perhaps what we uncover about ourselves is as compelling as the mysteries of the universe we aim to solve.